Hopefully I am live. Am I live? Looks like I'm live. Hi all. Took me a few extra minutes today to get everything ready just because I'm got some new technology and I'm just checking to make sure it's going to work fine. So if you see me a little bit nervous, it's just because, yeah, I don't want anything to go wrong. I see that my resolution looks a little bit different. So you'll be seeing some things that are slightly different here today. Hopefully you all can hear me and see me. So tell me yes, you can hear and see me in the chat. I'd be very happy to know this. Hi from India. Oh my goodness. Hi. Let's see. Finalizing. Yes, that's why I said finalizing things now. Good evening from the UK. Hello, Claire. Hello, everyone. Hi, Andy. Good to see you here. Mike Wallace. Thank you, guys. I appreciate you being here. Everybody saying 5x5. Julian. Oh, good to see you. Yes, Julian knows. And as well as a lot of other people. Hi, Bob. Good to see you here too. A lot of Patreon people here know that I am testing out some new technology today. So I have, as you will see, usually I use this as a controller. Instead, today, this is being used to say things like, hello. You have to deal with my really bad writing right now because I'm using my finger. But eventually I'll get like an actual stylus, so my writing will improve, I promise. But this is one of the neat things about, oh goodness, I have to do it this way. This is one of the neat things about this new technology is I'm able to do things a lot more wirelessly, and I'm actually able to scribble on stuff, which will help. I also hopefully have gotten rid of that 2-second latency. So when I always talk about being a drunken sailor, because I have to lean in to see if I point to something and then I realize 2 seconds later I'm pointing too far one way and then I have to overcorrect and I keep doing this like I'm staggering. That has diminished greatly. I am now only about half a second, a little bit less than half a second behind. So that should help immensely as well. And I have all of these folks here on Patreon to thank for that because they have encouraged me to do new things and have shown me places where I can go, like the NDI tools for OBS. And I have had to upgrade my systems and I've had to upgrade lots of stuff to get there. But it's apropos because I've now reached 500 patrons on my on Patreon, and it's just wonderful. You guys have made all of this happen, and I am so forever grateful. So I'm bowing and bowing to you. Thank you so much. And I use everything that you give me to turn around and make this setup even more profitable for all of us in terms of education and learning. And I'm just very grateful for you all. Oh, good. I'm glad to see Jerry Ryan. Hi, Jerry. Thank you. Jerry, be nice to Jerry. And Mike Richardson, if you see him, I haven't seen him chime in yet. But those are the moderators for this session. If you are not being heard, you've put your question 10,000 times in the chat and I still haven't seen it, ping one of those guys, because anytime I see them in the chat, my eyes lock in to see what they're saying because it's very important. So, oh, good, Mike, I'm glad to see you're here. So either of those guys, they're the main go-to people. They also have access to me directly. So if something goes wrong, I do have my cell phone on. They will call me. And if anybody wants to know the hilarious story behind why I keep my cell phone on during mini courses, go back to one of my early ones and watch 17 minutes of silence where my mic went out and I didn't know. And everybody in the chat was screaming at me, but I was too busy teaching to look. It was, lessons learned. So I do keep my mic on, and Mike and Jerry both will. Thanks, Jerry. I see that you said glad to have the new system up and running. Yes, they will make sure that your voice is heard. Also, be good to them, and don't be, rude or mean or say unbelievably inappropriate things. This is a very positive environment, and we all nurture one another. No question is silly or stupid, and I don't like to see kerfuffles in the chat. Okay, everybody has an opinion. Everybody's opinion is important, but don't start getting personal and attacking each other when you disagree. That's not appropriate. Okay, and Mike and Jerry will boot you. So put you in a timeout and then boot you if you don't, be nice. So. Okay, so it looks like everybody can see me, everybody can hear me, Everybody's saying, hi, I love this. And so I will begin to get started. Here's the cool thing about this one. Okay, so if you're new, um, this is the second installment in the basically what we're talking about is the ionosphere. Okay, so if you have never seen a mini course before, this will be slightly advanced for you. You probably will still get something out of it, but you can go to my YouTube channel and look at the mini courses. And in each mini course, you'll see they're arranged in a series. Each set of mini courses has its own course number, like P or I or M, right? This is the I series for ionosphere. And you'll see also that there are prerequisites, right? So if you start at the very beginning, there are no prerequisites, and then each kind of course builds on itself. We are now at the point where we are at the second chef, and the second chef is really basically the near-Earth space. And we've gone through the Earth's magnetosphere and down into the ionosphere. And so all these folks that you see behind me here on the mini course, actually, that's interesting. Hopefully I'm not backwards. This feels backwards. I guess not. Everybody who is I have to look at things in a mirror. Everybody who is one of the mini course patrons, I thank you so much. These are all the folks that get me to teach all the mini courses in a very particular way that makes they basically dictate what course material will be there. They also get their questions answered first, and these mini courses would not be possible without them. So my gratitude goes out to each and every one of these people. Your generosity is just amazing, and I'm just, I'm so honored. So if you want to kind of help steer what directions the mini courses take, then please become a mini course patron, and your voice will be heard quite loudly. And then also, of course, a huge thanks to all of my VIP steering committee. You'll see Jerry and Mike are both part of my steering committee. We also have Tomorrow in there and Matthew Shipley. Matthew is a Radiant Star member. He's gone above and beyond all expectations and become a huge donor. And I appreciate that very much, Matthew. So all of these people, they get to see me once a month, actually more than that, because they all have access to my cell phone. And these are the guys who steer the ship, guys and gals who steer the ship, and basically say what direction I'm going to go next, and help me figure out what is the best direction for our community. And they are amateur radio operators. They are, as you can see, Adrian has joined us. They are space weather hubs and aurora photographers. Some of these people, like Matthew and Adrian, for example, they actually have their own space weather communities, and we're trying to figure out how to link these communities now into a much bigger network. So we have locales that we can then dish out space weather information that's relevant to that local community. And so I'm really becoming grateful to a lot of these folks, because they're all helping build this network in a very savvy manner that answers the needs of the community. So with that very long preamble, I just want to make sure that you all understand how not just how deeply grateful I am to all these people, but just that really there is a massive community behind all of this, and we really are doing it with the community's interests in mind and at heart. So, okay, so everybody is good, and sub, yes, thank you very much, absolutely. And can anyone recommend an interesting book for my niece who is studying astrophysics? Oh my goodness, astrophysics. That's a slightly different topic than space weather. Astrophysicists look at stars that are very, very far away, and we focus in space weather. We focus on not just our star, but also how that star's environment affects places that we can actually hope to travel to someday. So that they're slightly different topics, and I'm not very good at looking at astrophysics, but there are a ton of books in astrophysics. I would imagine JPL is a great place to go for children's. I know they have an entire online series of books and worksheets and things like that to help teachers. So you might look in and around JPL, NASA JPL for stuff like that. At any rate, okay. So if there's no questions, I will start getting going. Oh, good. Space Girl Heidi, you're here. I will start getting going right now. Let's see. Mike, you said archive 16 of the previous mini courses. Yes. Thanks, Mike. Excellent information. And you can actually see all of that stuff right there on my channel. Okay, so whoops, let me go, now that I've done that, let me go to where, I'm going to skip forward to where we actually are. Last time, and you'll see some interesting things this time, because I've actually had a few people who have asked me specifically about the Comet Met-Ed modules. These are the basically meteorology education modules from NCAR and UCAR. And there are several of you who have actually used them periodically. And so I will actually bring a couple of them up because they're very, very useful when it comes to looking at the ionosphere. As I've shown before, the ionosphere is an extremely complicated monster. You think? Look at this. And if any of you have seen, I've described it as the upper atmosphere is kind of like this multi-layer cake. And you can imagine with all of this stuff, and we did talk about this particular slide last time, but I'll start off with it this time. You can imagine with all these processes going on, and most of this stuff is stuff that's happening from above, coupling down into the upper atmosphere. But some of this stuff is actually coming from below. And we'll talk more about that today. But if you can imagine that with all of this complication, it can make trying to understand what the ionosphere is doing at any one particular time and at any particular altitude extremely challenging. And so when you look up at the blue sky and you think it's just this homogeneous, even blue sky, and it's just air that kind of gets thinner and thinner as you go up, and that's all it is. Oh my goodness, are you wrong? I mean, it's unbelievably complicated, the types of processes that occur. And even more so, it's complicated because we go from a completely neutral atmosphere down below to a completely charged atmosphere above. And as you change from one regime to another, suddenly you get the Earth's magnetic shield and everything and all the electrodynamics suddenly becoming a part and parcel of what is going on in terms of moving and forcing all of that air that's no longer air, it's a plasma, forcing that around in different patterns. And we'll talk about that today. So in a nutshell, we were talking about all these processes, very, very, top level stuff, but you can just imagine, let me overwhelm you for a second, right? You can have all of these different processes like gravity waves and scintillation and plasma bubbles and winds and turbulence, excuse me, that complicate how this multi-layer cake actually function, right? But then you also get stuff from above, like different, just the day-night changes, having sunlight on one side of the atmosphere but not on the night side, right? And then having that rotate and spin around, then that changes things. So again, it generates waves. You can get conductivity changes, density changes. You get currents that are electromagnetic that we'll talk about these today. And then when you get, and that's just when the sun is quiet. Imagine that you add on top of that storms from the sun. Oh my Lord, right? Then all of these things change. And if you're an amateur radio operator today, I'm going to try to give you a hint of, especially if you're at high latitudes, a hint of something that you've probably not recognized. But it will make you, hopefully it will inspire you to want to look at the solar wind that much more closely, like all the time. Because you'll find that as the solar wind changes, especially in its magnetic field configuration, this region up here changes dramatically. Okay, and I'm going to go into that in pretty great detail. So, so you'll understand when I put this down here last time, I said, until models improve, the WHISPER reverse beacon network activity remain among the most reliable ways to probe the real-time ionosphere for radio propagation. And after this course today, you should pretty much understand why this makes sense, because you'll get a much better feel for how incredibly complicated it all is. Okay, let me just check. Somebody said something to me on my phone. No, it looks like I'm okay. And the news is going nuts about the ridiculous solar storm grays that we're having. Can you believe people in the media they're hyping it? It's just nuts. I don't pretend to understand it. Okay, anyway, that's neither here nor there. All right, so where I kind of left off last time was that we had talked about these things up here, right? This kind of upper level stuff. Oh yeah, I should be using my little chalkboard, which I will in a second. Not yet, but I will. But believe it or not, there's actually a lot of stuff that happens down here, and you don't really see it here. I think they might actually put it, yeah, you can actually read one of the words right here that says equatorial anomaly. Okay, if you can read that, that's great. But they're not really showing the equatorial anomaly. But if you're at low latitudes, I mean, I'm harping on high latitudes, but there's an actual band in low latitudes that's a problem too. And that's this thing, right? You can actually see it. So here's these are actually images of the Earth, and you can see the stripes. So let me use my thing. We'll see if I can do it. So you see there's a stripe there, and it's backwards. See, this is hard for me because this is actually backwards from what I'm used to, right? I'm looking in a mirror. So there's a stripe there. All of those stripes as they go down, these stripes that go down, and then down, and then down. These stripes here, those are actual passes of a spacecraft. Okay, so don't. Actually, I thought how I did that was this way. I have to remember how to do this. I thought I took it off that way. Maybe I didn't. Okay, so each one of these is a ribbon that passes down from basically a spacecraft passing over and taking observations. So don't look at the fact that these are like blue, these ribbons are actually part of the observation. They're not really. That's just simply the swath, the view path of the spacecraft. I get a lot of people getting confused thinking these black holes that go vertically, that's actually part of the actual phenomenon. It's not. It's just what we see. What we see is the spacecraft passes. The actual phenomenon is this light blue stripe that goes across. Okay, so kind of smear it out a little bit in your mind that this is actually a continuous thing and not this strange vertical ribbon striping. Okay, so this northern hemisphere stripe and then this southern hemisphere, stripe, these are part of what we call the equatorial anomaly. And what they are, you're actually seeing denser electrons. A denser amount of, the more electrons in this region, both in the north and the south. And it's due to something called the fountain effect that has everything to do with the Earth's magnetic shield. And this has nothing to do really with inclement space weather. This is just normal, right? This is stuff that just happens anyway. And it has everything to do with the fact that when you have electrons, when you strip away, when you go away from the neutral atmosphere and you go up into the point where you're getting ions, when you're getting into the point where you're getting, right, this plasma. And I don't want to have to go back and define what a plasma is, but it's basically take your neutral atmosphere and suddenly make it charged. And when you do that, right, you're stripping electrons away from ions, and basically the molecules in the upper atmosphere. And what happens is that suddenly, because now these particles are charged, you have positive ions and then you have electrons. Suddenly these particles go, oh, there's electric and magnetic fields up here. And they're looking around going, whoa, there's all these forces on me now that I never knew even existed, because when they were neutral, they didn't care, right? Neutral atoms, neutral molecules, they don't care. Electromagnetic fields just do what they do. And all they care about is if they're being bumped into or knocked around or being, having a wind pushing against them. But once you're charged, you feel all of that. You feel the wind, you feel being knocked into, you feel all the same stuff you felt when you were neutral. But now there's this whole new set of forces that's on you too. And it's like, oh my gosh, boy, I'm really getting nailed. So suddenly these electrons and these ions start moving. They start feeling these forces that and start moving in very different ways than they did when they were neutral. And that's what you're seeing here. Because down here, we have very strong magnetic fields, really low in the upper atmosphere, and they curve a lot. And those magnetic fields, when they curve basically from the south into the north, or vice versa. You see what I'm talking about here? See how they kind of go from one ribbon to the next? Those curved magnetic fields, right? If I pull out my slinky, my ever wonderful slinky, the Earth's magnetic field, remember we talk about the Earth's magnetic field being kind of like a toroid, right? If the Earth's sitting in the middle, right? So these magnetic field lines curve around, right? They curve around like this. So what you're seeing is an effect caused by the curvature of the Earth's magnetic field and the strength of it, the strong curvature and the strength of it down at low latitudes. What happens is that near the equator, the electrons are forced to move up, okay, straight up out toward you. And then when they get to a certain height, and they because they're being pulled back down by gravity, there's all sorts of other things, they begin to kind of fall back down. But as they fall, the forces on them force them to go to either side. So they bubble up at the equator because of the forces of the magnetic field. But then when they get up here and they need to fall back down, they fall back down according to which side of the equator they're on. Okay? And they fall both in the north and in the south. And so you get these enhanced ribbons, both in the north and in the south. Well, in the north and in the south. Okay, on either side of the equator, of the magnetic equator. That's why the ribbons are bent. Remember, the Earth's magnetic shield, whoops, I should do it this way. The Earth's magnetic shield is bent is tilted relative to the geographic equator. So what you're seeing is the mapping of the Earth's magnetic equator, and that's why it looks tilted here. And so these bands follow that same kind of tilt. Now, this is a problem for amateur radio operators simply because when you have changes in the total electron content, you get something called gradients, right? Gradients are changes, rapid changes. So you have high electron content here, low electron content here, and also low electron content in the equator, right? And then high again, and then see what I'm talking about with multi-layer cake, right? We get it in so many different ways. So if you are an amateur radio operator stuck in here, oftentimes you can maybe send a signal through this mess, but you can't get anything back. So you're stuck sending out signals. People out here can hear you, but when they try to contact you back, forget it, right? This is why de-expeditions oftentimes have such a trouble when they get in regions that are, low latitudes, but are within this equatorial anomaly. And this is a dayside phenomenon mostly like especially late afternoon is really bad. But during solar maximum, it gets worse because you get more electron flux. So the gradients get more intensified. Okay. So you'll either have a situation where you can send a signal out and it gets through, but you can't hear anybody coming back, or vice versa. You can hear everybody, but you try to send a signal out and they can't hear you. And it has everything to do with scintillation. Okay, and we'll talk more about scintillation and some of the causes of it. And then we'll even talk about, you guys see these striations, right? Like this little striation in here. Look at all these striations. See all these all this structure in here? Yeah, there's something called plasma bubbles. And a lot of those plasma bubbles actually cause that. Plasma bubbles, trans-ionospheric disturbances, there's all sorts of things that cause ripples in these ribbons, in these stripes here. And those themselves also are sources of scintillation. So you get sources of scintillation within sources of scintillation within, right? You're starting to see how complicated this gets? And I know I spent probably way too much time on this, but it's something that a lot of amateur radio operators don't even know exists. And yet this region can both hinder radio propagation, but it also can help. This region is also what, if you're in high latitude or mid latitudes, for example, in the north, you can actually surf. If you want to do DXing from, let's say, here to here, down here, let's say, you actually can surf and bounce off this region and allow a neat kind of skip, transhemispheric skip, when you have this region well formed. So this can actually help propagation, typically if you're outside it, to do a transhemispheric jump. But if you're inside it, it causes problems. Right? It's very similar to being, for those who are at high latitudes and are inside the auroral zone, that auroral oval creates another kind of boundary that's oftentimes hard to get through, right? Similar kind of thing here, right? It has everything to do with these gradients in electron density. And you'll see, even when it comes to terrestrial weather that have a tendency to cause these types of striation, these little things, this is one of the reasons why people deal with sporadic E and all these things that actually are coupled to terrestrial weather, why it affects radio propagation so much. It's because it's either creating layers, it's removing layers, it's creating gradients that then cause scintillation or actually help to help to facilitate skip. I mean, there's all these really nuanced kind of things that we don't completely understand yet, and are very stochastic in nature. So it makes the ionosphere extremely difficult to deal with. And when I talk about it here in this, one of the things that we always have to deal with are things like, not just things like signal power fades and cycle slips, but also when it comes to GPS, for example, or GNSS, you have things like, not being able to get a lock on your receivers, right? And you need 4 of the satellites to be able to get a lock. So this doesn't affect not just skywave propagation, it affects propagation from space through this region down to the ground, right? And so you have a bunch of issues when it comes to trying to propagate through this mess, whether it be from a ground transmitter or a space transmitter. And this is one of the reasons why Brazil, it's so hard to get GPS working properly, especially at certain times of the year, certain times of the season, certain times of the day. Oh, and in case you're interested, this is GUVI data, right? Aboard, this is GUVI aboard, I think, DMSP. I don't know which DMSP it is, but I don't think I have it said. Probably 17, maybe even 18. Okay, so hopefully that kind of is like a I don't know if that's drinking from a fire hose. I always worry about this course. The ionosphere is incredibly complicated, and part of it is not just the atmosphere itself, but now for those of you who recall how migraine inducing the currents were when we talked about them briefly in the magnetospheric version, well, we're back to doing that again. So, see, this is what I should not do. I need to take hopefully, nope. I let my pad go to sleep. Bad girl. So now I have to restart the NDI. See, these are the errors that I should not let happen. So then you're probably going to see a big funky blue screen behind me. Yeah. Okay, got it. Long as it starts up again, I'm cool. Does anybody know off the top of their head how to not let an iPad go to sleep? Do I have to go to settings? I probably do, don't I? Probably shouldn't do that while we're here. Whoops. Let me go back to my notes. I'm sorry, guys. Well, this is the fun part of learning how to use stuff. Is I don't. There we go. Okay, hold on. I'm not super smooth at all of this, but I have a feeling I'm going to use my pad a little bit when I'm talking about this, because we might be discussing what direction currents go, and I don't have those necessarily labeled on the diagram. So hopefully I am not completely like losing everybody yet. Let me know if I'm losing. And I know a lot of comments scrolled by, but yeah, radio operators are good at using skip. Yeah, this is the thing, is I don't want to end up losing radio amateurs here, because it has. Oh, Deborah, I guess Deborah's video froze for a second. Hopefully she got it back. Yeah, settings and change your sleep time. Okay, let me do that, guys, because I really don't want to. While I find out whether or not I've lost anybody, let me go to settings. These are informal, remember. Okay, so settings and sleep time. Where's sleep time? Oh, come on. It's not that easy. Where is sleep time? I'm not seeing it. As you can tell, I don't use iPad very often. I'm getting into apps now. It's in general, or is it in control? Wait. Do not disturb? No. Sounds, notifications, screen time? No. What is that? Anybody know? Oh, goodness. Settings, display, and brightness. Oh, that will actually help if I do. Can I do that? Display and brightness. Sleep time. Is there a sleep time? True night shift, auto lock, text size, bold text view. Come on. No, there's nothing in here about that. What if I pull, can I pull that down? I wonder, really fast. No, that doesn't work either. Is there something in here? What is this? The moon. What is that? Do not disturb. No, that doesn't help me. I don't know, guys. Settings first. Settings, display and brightness, auto lock to off. Oh, okay. That's how I do it, huh? I go to auto lock. Oh, got it. 10 minutes. Ah, never. Haha. Got it, guys. Thank you. Excellent. Thank goodness there's some iPad savvy people here. Okay. Auto lock is off. Whew. Thank you. Okay, good. Yes. So I try to watch your videos and love what I learn. Oh, good. Okay. And nobody is lost. Am I cool? Because I just want to make sure that I've not lost anybody yet. It's because it's going to get a little bit more complicated. This may be one of the most complicated courses I've done yet. I hope not, but it might be. So what we want to do is we want to start talking now about currents. Okay. Now, if you've watched the magnetospheric courses, the M series, you will know a little bit of this. These images should not be completely alien to you. However, we're going to go into them a little bit more deeply, and I will use some nice videos here, because I'm going to go to the Comet Met Ed things to show you like some nice animations and stuff that will help. Okay, so if you recall, we have the, and I'll just start with this big picture here. This is one you guys should probably remember from the magnetospheric thing, but I'll talk about it again. So we have, this will be cute. Watch this. Let's see. So I should be able to draw down here. Yeah. Okay, so we'll draw down here the sun. Okay, and it's blowing solar wind this way. Do you see the sun? I should have drawn it yellow, shouldn't I? Oh, well. Okay, so I've got the sun, and I'm drawing that way. Now, if I'm going to back up one, because I've got that arrow blocking what's going on. But if you see this right here, so this, what's happening is the sun is blowing the solar wind toward Earth, okay? And this is the Earth's magnetic system with currents, and kind of with this gray thing is like a capsule, okay? Like a capsule that's surrounding Earth, all right? That's kind of like that comet. Remember we talked about in the magnetospheric courses, we talked about that big long comet tail. This is kind of showing that, okay? But now we're going to get down into the nitty gritty. So when the sun is blowing the solar wind toward us, believe it or not, because of the magnetic field and the electric fields inside the solar wind, that's blowing against the Earth, and the Earth has its own magnetic shield. When we get to a point where the two touch each other, the two reach each other, the solar wind slams into the Earth's magnetic system, right? We have a bow shock, and then we have all of this diversion of material around, basically you have to have a shock wave to slow the solar wind, the incoming solar wind, so it can divert itself around this obstacle, this massive obstacle that's the Earth's magnetic system. And when that happens, you get currents that are set up, okay? Now, we're not even inside the Earth's magnetic system yet. We are at the magnetopause, which is the edge of where the solar wind hits the Earth's magnetic system, and the Earth's magnetic system is not open, letting stuff in. It's actually stopping it. It's blocking it, okay? Because remember, the Earth's magnetic shield is a shield. It does stop stuff. And if you recall, solar wind doesn't get into Earth here. Not at all. It actually gets into Earth here through the cusps and through the tail, okay? So particles get slingshotted. Particles get slingshotted forward from behind. Remember that? Okay? All that whole funky chicken dance and all that stuff. We'll show a little bit more about that again today. This is the nice thing with me, is I do a lot of repetition. So immediately you have what we call a magnetopause current set up in front. Okay, so this current is actually, it's showing it moving this direction, but believe it or not, there's currents all over. Okay, and it moves, this current closes this direction, moves this direction here, and then it goes up and around in the northern hemisphere. And in the southern hemisphere, it comes this way again, comes this way again, and then closes the opposite direction. So so immediately what you should think of is that it's right at the equator of Earth, which is what this plane is. Okay, that's this cut plane where you got a vertical cut and then it goes slice, right? So you kind of take out that piece and you're looking at the interior of the system. This right here is Earth, right? And I could probably do a cute little, I'd have to find the Earth. Where is the Earth? Nope, that ain't it. Let me do that. Where are you? Nope. Let's see, I'd put it there and there. That was too far back. So here, nope, that's too far forward. I'm all inside it. Okay, so I think I know where Earth is. And let me just do, and I'll try to do green. Whoops, still too high. So this is part of the problem with me, is that I need to be able to get, oh goodness, and it's a mirrored. See, it's easier for me when it's not mirrored. So there's Earth. Goodness, goodness, goodness. Hopefully I'm close. Yeah, and you can't even read it. So here's Earth in here. Okay, I'm just going to color it in. That's Earth, okay? So if you guys can see that. So you're looking at the planet, right? And then these other lines, okay, and that's why I drew a circle around or in the planet, trying to color it in. I didn't want you to think that the planet was smaller than this. This is the actual planet itself. And then these lines here are magnetic field lines, okay? And then you've got something that comes around here. This line here, as it goes around, really is actually a current, okay? It's not a magnetic field line. So we have to be a little bit careful when we look at this diagram, because you do have, you know, all of this actually is a current, but you have field lines that are representing the dipole magnetic field. So if I were to take that slinky again, and map it to this region, okay, you're going to see, in a sense, part of that slinky goes look right there. If I can get my hand out of the way. And the other part of it goes right here. And if it weren't quite so floppy, you would see that, okay? Does that make sense? That's the Earth's magnetic field. Hello, hello. So that's the slinky part, right? And then that slinky extends further and further out. But because of the way a lot of these current systems are oftentimes what we call field aligned. And we'll talk much more closely about that today. And these field aligned currents, now this around here in this equatorial plane is not field aligned, obviously, right? If I have a slinky that's sitting here like this, there's no field that's going straight through, you know, that's aligned where this purple line is, right? So you have some currents that are field aligned, you know, or some part of a current system that's field aligned and some part of the current system that's not. And that's oftentimes why you'll see, you know, why you find these current systems, even though they're all connected, you find different names in different sections, because I've had questions about that before. So you can have, for instance, and I'll even talk about it for just 1 second. You see here it says region 1, right? This is oftentimes called a field aligned current system. But then you see that it's all connected to the magnetopause, right? It's all the same color. It's like, well, why do you call it two different things if it's the same current system? Well, because of in physics, in the magnetospheric physics, it's important that we understand the difference, because certain things are happening when the field, when the current is actually moving along the field than when it's moving perpendicular to the field, okay? And if you recall with the magnetospheric stuff, when we were talking about the bounce, the actual particle motions, we were talking about bounce and drift, and you know, all the 3 different adiabatic invariants. I know that's a mouthful, but they were different ways the particles moved. In this case, when you don't have field aligned, how you're getting these currents is through bounce and drift, okay? But here, the particles actually are spiraling just around the field and moving very much along the field lines. Okay, they're being guided by the field, but they serve different purposes. Okay, so back to the magnetosphere. You've got the magnetospheric current going across in this direction at the nose of the magnetopause, and then it will close by going up and over in the north and going down and over in the south. And you'll see it's like 2 different canisters stuck together. But then on top of that, and I'll show you an animation shortly, but on top of that, you can also see that we've got the ring current, right? And we've talked about the ring current before. Remember that? It was the current that is co-located with the radiation belts, with the outer zone especially. But it's low energy stuff, right? So it's inside that toroid, right? Again, I shouldn't keep the slinky too far. It's inside this structure, right? The particle accelerator, right? But in this case, it's the low energy stuff. It actually serves as kind of like the particle pool, right? The source for radiation belt, you know, energies, radiation belt fluxes, because this stuff can get energized during geomagnetic storms, during big storms. And it helps boost that flux of energetic particles in the outer zone, which then trashes the satellites. Okay, you guys remember? So this is why this becomes a bit of an advanced course, is because it's forcing you to put pieces of different courses together. So that's the ring current, okay, and that you'll see actually couples to these field aligned current systems. So you have a field aligned current system here and a field aligned current system here. They're region 1 and region 2. Okay, anybody who's ever studied physics, as soon as you think region 1, region 2 currents, you should be thinking aurora, because that is those are the main current systems that drive aurora. And if you recall, right, we get particles being slungshot from the tail that then go up into the magnetosphere. I always talk about that. I always talk about these particles are being slung up into. Guess what? Think they make part of that region 1, region 2 current system? Yeah, they do. Okay, so field aligned current systems are extremely important. And then down here, you can see even in yellow, the tail current. Okay, notice the tail current, okay, they call it cross tail current, is the same thing as the magnetopause. It goes the same direction. Well, that's because it's part of that closure. In the northern hemisphere, it comes this way and closes up over the top. In the southern hemisphere, it comes this way and closes over the bottom. Okay, and I might show that. Do I want to show that right this second? Yeah, I think I will. Before I go to this diagram. Okay. Why aren't you showing me where it is? Let's see. Here we go. So I'll make sure this is off. Let me make this big. So for those of you who don't know what the Comet MedEd courses are, they're pretty light. If anything, I wouldn't say they're lighter than mine. Whoops. Let me, I guess I probably should what do I do? Take that away that way? I forget how I make that go away quickly. Oh, I know. Okay, yeah, I think I remember now. I think I was just saying delete. The MedEd courses are the ones that they try to do their best to combine physics, some physics principles, with some decent animations, but sometimes they will get into the math, so they'll be more deeply entrenched than my mini courses, and then sometimes they gloss over stuff that I think is really important, and so they kind of they're good supplements for what I'm teaching, but I don't necessarily think that they would replace them. I don't think they're necessarily harder than the courses I teach. So I would encourage you, if you really want even more content than for what I give you, feel free. Go. They're free. They're at the NCAR, UCAR, and I could put a link in the description, or I can even go over them during a Q&A, show you where to go to get them. But they're very useful, and there's lots of different things that goes into the physics, especially the physics of the aurora, because that's what a lot of people are super interested in. And then they also talk a bit about just space weather basics, and even issues with like, why is SWPC important, and you know, some simple things like how do you navigate the products of SWPC, and a lot of it's really old. They need to be updated, but they're still useful, especially for the fundamentals, like what I'm going to talk about here. So if I flip over here, you can kind of see. Remember, we just looked at this, right? This is that cone. This is that cavity that I was talking about, and you got the magnetopause current right here, right? This is the thing that is going. In this case, we have it going from dawn to dusk. Okay, so in this case, we're calling it's an eastward current. Okay, so as the magnetopause current goes this way, you notice down here, remember I was talking, you have two different things. You have in the northern hemisphere, you have this one that goes this way. Oops, I'm making my hand too big. At least I don't look quite like a drunken sailor anymore, right? And I follow it down this way. That's how the magnetopause current closes in the northern hemisphere. In the southern hemisphere, you start here again. The magnetopause current, I mean the crosstail current, goes eastward, just like the magnetopause current does up underneath my arm here. Tickle, tickle, right there. And then, sorry, I'm goofy, I know. And then it closes over the surface, essentially, of the southern hemisphere. So it actually is completely opposite of the northern hemisphere. And for those of you who actually are meteorologists, this should feel really warm and fuzzy, because the same kind of thing happens like with Coriolis forces, right? When the Earth is rotating, you've got circulation patterns in the north that are opposite to circulation patterns in the south. Yeah, same kind of idea here. Not necessarily because of rotation, but because the way the magnetic field is oriented in the northern hemisphere relative to the southern hemisphere. So what you see is that a lot of the magnetopause current is serving to kind of create that closed boundary, right? And if and you can actually see too, it may be pointing straight eastward right here at the perfect nose, but as you get further and further up at higher latitudes, it changes, right? And it gets further this way and further this way, and until you get way down the tail, way down the tail this way, and it becomes almost completely perpendicular, right? This direction here, again, I'm mirrored, so it's kind of frustrating for me. It's almost completely perpendicular to the surface. Okay. Oh, and then the other thing I wanted to show is this is the equatorial plane, right? In Earth's equatorial plane. So that's what you're seeing here when you're seeing this flat line, right? That's cutting across the plane of the image. So what I'm going to do is I'm going to play that here a little bit. I'm not sure exactly when it starts. So they're showing different cavities. There we go. Hang on. Maybe I will let it go a little bit further so you can see some of the labels that they give, because they're not, it's not too intense. So you can see where the magnetosphere is. You got the magnetosheath, which is the stuff outside. So the magnetopause current flows in such a way as to separate and keep separate the stuff in the magnetosheath from the stuff that's inside the Earth's magnetic shield. They're pointing out the crosstail current, which is the same as on the nose of the magnetopause, as you can see. And notice, and I'll stop it here. Whoops, if it'll let me stop. Okay, let me back it up just a smidge. So this gives you a good feel for the depth of the comet modules as well. So as they're talking about the nose of the magnetopause, right, and they're talking about this current system that's going through, they're actually, look, region 1 currents, right? Okay, so we're going to talk about region 1 field-aligned currents. So part of this magnetopause system is actually closing in region 1, and we'll talk about that. And they're actually trying to show them right here. See these lines? Okay, and then notice this equatorial thing. Okay, this is part of the equatorial plane. Notice part of that region 1 is actually closing in here too. Okay. So you've got magnetopause current. So this is how complicated current systems can get, right? When it comes to space weather, you've got stuff closing on the outside of the Earth's magnetic system, and then stuff those currents are actually feeding in to systems that then couple into the Earth's upper atmosphere, okay? And also couple into current systems that are feeding into my purse. I don't know where my purse is. My husband is taking the dog to get a bath.
Won't get in my car.
Live TV, guys, live YouTube here. All right, it's this Christmas bath. The dog needs a bath, and yeah. Anyway, sorry, I'm still laughing. Okay, so this is from the tail. I'm not even going to look at the comments right now because you guys are going to be like laughing at me. So this is from, I'm trying to remember where I was. This is from the tail, right? And remember, when we have inclement space weather, we have stuff shooting forward all the time. Getting that's actually being I'm listening to this mess that's going on in the front. The stuff is being slingshotted forward, and it's going, it's going to go into the upper atmosphere through a similar kind of system. But even if we don't have that, even if we just simply look at the magnetic system in of itself without any real space weather happening, so this is the quiescent magnetopause, right? You see that there's actually active currents. So if anyone ever wonders why is there aurora, how could there possibly be aurora during? Sorry. That was probably a very funny scene. The dog not wanting to come, and he's yanking him, trying to, come on, you're going to get a bath. Sorry. Oh, gosh. Okay. Focus, Tam, focus. So even when you don't have inclement space weather going, there's still aurora. Okay. It's just quiescent aurora, and it looks a little bit different. But I just wanted to let you know that this is a lively system, irrespective of whether or not there's actual space weather going on. Okay, so you can see that. Now, when they're talking about region 1 and region 2, and I'll go ahead and pause again. It's a nice thing about what we're doing here. So they're actually they're trying to show you that the region 1, region 2. Oh goodness. I'm not going to step out. Hopefully you didn't hear that. Apparently the dog saga is continuing. So the region 1, region 2 currents are ongoing. I think something bad happened. I'm not really sure. Sorry for being distracted, guys. I'm not even sure what's going on. At any rate, okay, so we will talk more in depth about these region 1, region 2 currents and how they affect the aurora. You're going to have to give me an idea of how deeply you want me to go, because my problem is I could dive into the details so far that you get completely lost. We can get into things like Hall and Pedersen currents and just start doing things that are extremely complicated, and I don't want to overwhelm you. So here we're talking about, and they're talking about the plasma sheet now. I'm not sure that's important. I'm trying to see if there's anything else in this COMET module that's going to be super critical. I think that's pretty much the bulk of it. Right, so here I'm looking at the words. They're actually saying that, and here's an internal view of it. They're actually talking about, once again, that these region 1 and region 2 currents that you see here that we will go into in depth, they both enter at slightly different latitudes. If you see, region 1 is always always inside, and region 2 is always a little bit more, lower latitudes. And if you recall, okay, going back to L shells, you guys remember L shells from the magnetospheric thing? L shells that are at higher latitudes, they map to higher L shells, which means further out, right? And when you get to the boundary of where you have open magnetic field lines, those open magnetic field lines are the ones that are in the solar wind, okay? But when you get to the highest L shells, that means the very edge of the Earth's magnetic system. That is the first closed field line. Guess what? That's where the region 1 currents are, okay? They map essentially, not exactly, but essentially, to the first L shell. I mean, not the first L shell, the highest L shell, okay? And that's because they're mapping to the Earth's magnetopause, that magnetopause current, the edge of the Earth's magnetic system. So as far out as that Earth's magnetic system goes, that's where region 1 is going, okay? And as you can see, there's particles that are being shot all the way across the Earth's auroral oval, even through the middle. Most of these are electrons. You've got, and protons. There's electrons that are being shot actually perpendicular, that swirl around these current systems, strangely enough. So, I'm not even going to try to draw that. I'll take me half an hour to get there. So wherever these things actually penetrate, there's actually patterns, circulation patterns that go in, and we'll talk more about those in a minute. But notice that the region 1s are the ones that go in here, and I'll be talking about these quite a bit. And then region 2, down here, they're a little bit lower latitude, which means the L shell isn't quite so high. So if you were in my Millersville class, I would quiz you and say, well, what does that mean? Does that mean that they're mapping to the edge of the Earth's magnetic system? No, they're mapping just inside it, right? They're a little bit deeper inside. So they don't go quite out quite so far because they're at lower latitudes. They're more protected L shells. Region 1 is where the L shell is at the very edge. It is getting hit by the solar wind, essentially. So the current system, at least part of the current system that's feeding this, is actually literally at the very edge of where the Earth's magnetic system meets the solar wind. All right, let's see if there's anything else that I want to tell you about it. Oh yeah, you're starting to see a little bit of that. Oh goodness, I didn't realize that this thing, I probably should, let me back off of this. So this will be the next bit of complication. And remember I was talking about the currents. So the stuff you see in orange, that's the main currents, but in the Earth's upper atmosphere, these currents that are called Pedersen currents are mainly for ions. And then the yellow, these are what we call the Hall currents. They're the circulation patterns I was telling you about the electrons. Okay, so the electrons are basically doing this, and the ions are basically doing this. And believe it or not, these patterns change depending upon what the solar wind is doing, right? Because it's all being this is region 1 currents. These are mapping to the edge of the solar wind. And this is why current patterns can change so dramatically depending at super high latitudes, depending upon what the solar wind is doing, because there's nothing protecting them, right? Unlike at mid latitudes where it's kind of the Goldilocks zone, you're kind of protected because you've got a buffeted, you're buffeted away, and you've got other current systems that are kind of taking care of that for you. But region 1 currents can get pretty crazy. All right, let me see. I do not want to go in depth to this level. So do I just do this? Yeah. All right. So before we dive into that too deeply, hopefully I'm not, why demand a video introducing the dog? Not right now. He's in the dog house right now. I think he did not want to go get a bath. From what I can tell, the dog is in real trouble. So that's why oh my goodness, Jim, you go deep, you want to know it all. I don't have people kind of like completely shell shocked right now, like drinking from a fire hose. Dog walks in the solar wind, right? Will it create a colder winter, like a mini ice age? Will this create a colder? No, this stuff goes on all the time. So this kind of thing it's always occurring. Taking notes. I'll get class tips here. That's funny. Okay. I see lots of dog emojis. Oh goodness. So the dog, yeah, that was probably one of the most shaken I've ever been in a mini course, because I almost couldn't get back on track. Dog biscuits. You guys, is anyone petting that dog? Not right now. Oh God, come on, guys. No, like I said, the dog's in trouble. Okay, so yeah, doggy in the doghouse. Are they weaker as they shift? Yes, we will talk about that. I will show you, and I will show you when we go back to the Comet MedEd animations. I'll show you some neat things that change when the solar wind changes and how dramatically it changes the currents. And then some of the different types of aurora you get. You can actually get something called horseshoe aurora or theta aurora when you have northward solar wind, northward, what we call northward IMF. And yeah, it's a really complicated mess. So if you happen to live at high latitudes and you try to do radio propagation, this may help you understand why it can be just so such a disaster. And hopefully what it can do is that you'll start looking at the solar wind and seeing what the solar wind magnetic field is doing as it's hitting Earth. And then you'll know, oh, okay, it's north and westward. So that means I should think about propagation this way. And believe it or not, that will actually make sense to you by the time we're done with this class. So, okay, not at all keeping up. Oh, good. Makes sense so far. Thank goodness. Okay, is that the X and Y on the BZ data? Yes, not the BZ data, the B data, right? BZ is considered the Z component. The BZ component or BZ is considered the BZ component. So you have BX, BY, and BZ. So, right, you have BX, which would be, if you're the Earth, BX would be pointing radially straight towards you or straight toward me if I'm the sun. Okay, that's Bx. By would be the component that's pointing east or west, so toward dawn or toward dusk, if again you're the Earth. And then Bz, of course, points northward or southward. So yes, we are talking about the magnetic components in the solar wind. When you look at solar wind data, those components make all of the difference when it comes to how the upper ionosphere, the region 1 currents and the region 1, region 2 currents look at really high latitudes. Okay, and then that, of course, as we talked about already, with those currents going, those are electrons, right? And so when you think electrons, right, you think currents, then you think electrons, then you think electron density, right? And when you think electron density, then you can think propagation for radio propagation, and you think gradients, changes and all that stuff, because that's what facilitates radio propagation or squelches it completely, causes scintillation. Okay. Oh, and that was you, Jerry. I say you said that, yeah. So in theory, could a solar flare cause them to reverse? I'll show you what causes them to reverse. And it's not a solar flare. Where solar flares, remember, if you've seen the courses back on solar phenomena, solar flare really is just the sun screaming, right? It just screams. It can scream as loud as it wants, and it really won't cause that much, any real reversal. It does cause a huge ionization in the upper atmosphere, but it's pretty homogeneous. It doesn't actually cause it to reverse. Although we can get, and I don't know if I'm going to show you that detail. When we start getting and talking about seasons, how seasonal variations affect radio propagation, because there's something called an ionospheric anomaly, and the anomaly is that you actually get better propagation in the winter than you do in the summer. And the reasons for that are multifold, but it's non-intuitive, because you would think with more TEC, more ionization of the upper atmosphere, you should get better propagation. And it doesn't actually work that way, because there's other things going on that have to do with heating. And so, yeah, I think I've got to think about whether I want to go to that extent. We might save that for another discussion somewhere. Again, it's how deep into the weeds do you want me to get? Right. Yeah. How this affects the human body is for those people who are extremely sensitive, I don't even have a clue yet. I mean, there's medical professionals working on this, and even they're just trying to get a handle on how space weather events affect things. Not really sure how it ends up being, how it ends up affecting everybody from a physiological standpoint. Okay. Yeah, I would blow Joe Rogan's mind. Yeah, I might make him say, I'm never going to talk to her again, ever. Okay, good. I'm so glad it's making sense to everybody. Okay, because I'm very, very sensitive to that. We need to have a class strictly for the radio guys. Yes, Mr. Burns. You know what, Bernie? We need to figure that out as you're on my VIP. You're on the steering committee. So that definitely needs to be a discussion to see whether or not amateur radio operators want one that's straight for them. Of course, it excludes a large part of our audience. So I'm not sure that we do that. There may be another way to go about it. I don't know yet. But once I get through all the basics, the space weather basics for the ionosphere and the ground, then we can talk about advanced topics, because we're getting there. Seasonal changes would be a good spin-off course all by itself. I agree, Chris, it could be. So, that's something else that we need to talk about. Maybe these are advanced topics that we leave for that time. I can just mention them here and then we move on. Thank you for explaining, and I would like to hear about it if you get around to it. Yeah, we'll discuss that near the end. Okay. Yeah, chatting with a neurologist about space weather in the brain. Yeah, there is no doubt there's issues for people who are physiologically sensitive to electromagnetic fields, and there's a lot of people that are. People are finding that out just from cell phones. There are some people I know who have heavy metal poisoning. I've talked about this before, and they get rashes on their hands every single time they use their cell phone. They'll just within a few minutes they'll get rashes on their hands. It's amazing, and and people who have metal plates and screws, people who are becoming more cyborg than human with all the medical advances we have. And now, the idea of having neural shunts, Elon Musk wants to do this AI stuff where we're actually putting in, electronics in our, in chipsets in our brains. I don't think he's thought for a moment about space weather impacts, like going up in high altitude flights and getting a single event, a single event effect, a bit flip or something like that. How is that going to affect you now that this thing is plugged into your brain? I mean, it's like, whoa. I mean, that adds a whole new level of complexity when it comes to neurological conditions, that are being induced by galactic cosmic ray penetration or solar energetic, these radiation storm penetrations, right? I mean, you're going to be just as affected by space weather as the avionics of the plane that you're flying in. These are very, very astute questions, and they're coming up faster. The questions are becoming more relevant. It used to be the realm of sci-fi and Hollywood, and now we're really needing to start thinking about these things. So it's a whole nother reason why space weather needs to be elevated to the level of terrestrial weather, because it's becoming a point. We're getting to a point where we're not going to be able to ignore it anymore, especially as we're integrating these medical devices into our bodies. It's getting kind of scary, kind of cool, but scary. So we got to make sure we do it smartly. Anyway, that was a side note. Sorry about that. Okay. You were offered a chip for epilepsy. Yes. See, this is what I'm talking about. Right. Yeah. And I know other people, a member of my VIP committee, for instance, has some electronic enhancement, augmentation for medical reasons. And I mean, we have to start thinking about this, because it's not just, the maybe it wasn't as much of an issue when computers were just starting, because I mean, we still use tubes, and we still used analog equipment. We still used very, systems that required, monstrous voltages relative to now. Now we've miniaturized things to such an extent. They use just these tiny, not even millivolts. I mean, we're getting almost close to the point where we're going to start using nanovolts, here soon. And when you have these tiny potentials in these tiny currents that are being used as real signals, and the signal to noise ratio is being brought down so much by this advanced technology, that now space weather is suddenly in play, because these tiny things that we were able to ignore before as being part of the noise floor is no longer part of the electronics noise floor, because the electronics is getting so quiet that now space weather, it actually can sense space weather effects. And that's, I mean, that time is coming faster than we could possibly imagine, and no one's even aware of it. So cochlear implants, excellent example. So epilepsy, cochlear implants, all sorts of things, even cybernetics for eyes. We've got to start thinking about this stuff, and we just don't do it yet. Okay. Yeah, laser disc before CT. Right. I mean, it's same kind of idea. Okay. Back to this. Sorry for that little bit of a digression there. Okay, so if I now, after looking at the magnetosphere kind of this way, when we're looking at it from this perspective, and you saw that animation, let's kind of just break it down into some simple basics. I always like giving multiple pictures, so that if you guys ever have to go look at journal articles, right, and you're trying to understand them, there's all sorts of ways of drawing current systems. And so if the more things I show you in these mini courses, the better equipped you feel to anytime you get hit with a diagram that you've never seen before. So this is another version of the diagram. And we're sitting here, this says Earth's night side, in case you can't read it. So imagine the sun completely, on the other side of this image. Okay, so you're looking at the tail of the Earth's magnetic system. And now you see the circle, right? This circle is essentially the edge of this shield, right, back here in the tail. Okay, so really, if you put this like this, where the equator is, okay, you'll have a current system going this direction, and then in the north, you can see the arrow. The magnetopause current comes, it hits here in the middle, and closes this way. Okay, I might be able to draw that. Let's see. Think I can do it? I don't know. So it's on this side. Where am I? Oops, let me do, whoops, I need this. Nope, too high. And let me do red. A little too low. What about there? Let me go straight across. So if I do something straight across like this, and I go around, too high, but you guys get the picture, okay? So you've got, in this case, you've got a current system that goes this way. Whoops, wrong, because I'm in a mirror. See, this is the problem for me, is that I have to, does anybody know if YouTube, when you do this, YouTube doesn't require you to use a mirror? Because when I do this on YouTube, it's very frustrating to me that I have to look at myself mirrored. When I teach Millersville, I don't look at myself mirrored, and I've gotten much better at doing it. Oh, I did it wrong, didn't I? Arrows the wrong way. I've gotten so used to looking at things in such a fashion that I don't, I don't need the mirror, and now using the mirror confuses me. Isn't that weird? You'd think that mirrors would be so natural, but not when I'm teaching. They don't seem to be natural. So that would be essentially the current system for the magnetopause on that side. Now, when I draw it for the southern hemisphere, and I'll try to draw it a little bit better. Much better. Again, the magnetopause current goes the same direction. Okay, in this region here, because this is the crosstail current. I'll do yellow right here. Okay, so this whole thing is considered the crosstail current. That's actually a terrible color, isn't it? Let me do, what would be a good color? Let's do green. There's the crosstail current. Can you see that? Okay, so that whole thing is a crosstail current, but it's combined both in the north and in the south. So when I continue drawing the current system in the south, right now the currents flow this way in the magnetopause. And this is what we saw in that animation. Okay, that you have the northern hemisphere doing that, the southern hemisphere doing that. Okay, and that is the magnetopause and crosstail current system. Okay, but notice that crosstail current, right? That crosstail current actually ends up flowing all the way through this whole region, right? And it's also in the same plane as the ring current. See that? So the crosstail current can actually help feed that ring current if we're not careful. And it goes all the way down. As long as this magnetotail exists, it goes all the way down until we get to what we call the X line. Remember that slingshot? That's one of the X lines. We typically have a near Earth X line, and it's called typically an NENL, near Earth neutral line. And then we have the same thing further down. That is essentially the back edge of the Earth's magnetic system. It finally closes completely. But that's hundreds of Earth radii downtail. Whereas the slingshot I'm talking about is about 30 Earth radii downtail, give or take a little bit. Okay, so let me erase this. And I think I do that by doing this. Delete, whoosh, yay. And I'll delete this one too. Oh goodness, look at me. I got to get rid of a few of them. That's how I had remembered now how to do it now. Okay. So you see that, so that's how this diagram maps onto this one. Okay? Because this is essentially that same thing I showed you in the MET-Ed module. That was all animated. That's that same capsule. But notice now, the nice thing about looking at it this way as opposed to this way is that this is really complicated with lots of other lines. This just essentially has the current systems on it. Okay, so looking at that outer ring, the outer blue ring as the magnetopause, the edge of the Earth's magnetic system, you now can see more clearly how region 1, when I said region 1 maps to the magnetopause, you can see it right here. Okay, and believe it or not, the region 1 currents, if it shows, they actually take multiple hops. And maybe I'll pull my thing in. So imagine coming from here. Actually, you know what? Let's start at the magnetopause. Imagine coming from the magnetopause in the north, right? Down this way. And then coming right to here, which is right at the crosstail current, right at the edge. And now you get diverted up into here. You go this way. and you come in, book, and then you go across. Remember that closer diagram actually showed there's a connection, the Pedersen currents cross, and then you go out the other side. If I can follow my hand. Do I trust myself to do that on the scratch pad? Maybe. Down, right? And then you are back at the magnetopause on the other side. So this side over here, looking from, we're on the Earth's night side. Look, we're looking at the Earth's night side. So this side over here is dusk. This side over here is dawn, okay? Because the sun is behind us. So at the dawn side, you get diverted again to the Earth's magnetopause and back. So you can actually close this way, right? Currents like to close. They like to go down in loops. So that's one way that region can close, okay? Now, obviously, again, this is all happening right at the equatorial region, right? And we have that crosstail current. So the region 1 current system, is only it's only diverting part of that crosstail current, right? The rest of it closes in that crosstail current region that I had. I probably shouldn't have erased that nice diagram that I had. But if I can remember how to do it, let's see, what pen do I have? I have red again, okay. Maybe I shouldn't do, well, I'll do red again. So if I can figure out where I am, oh, not too bad. Okay, so here's this region, right? So that's the crosstail current region. And I might erase that red in a minute. But what we're looking for, and I'll do it in green, why not, is that I go from here, hopefully. No, not you side, this side. Yeah, see, mirrors. That mirror just bothers me the poop out of me. So we're going kind of like this. Whoa, too high. Like this, maybe? Okay, hold on. I'll get there. Yep. In like that, over, and then out again. Too far. And then up and around. Looks like a skull cap. Right? And so if I, please tell me I'm doing it right. Nope, see, the mirror. That mirror bothers the poop out of me. Yep. Right, so I'm drawing arrows again. And remember, when I get a pen, this is my first time doing this, so this is the worst I will ever be at this pad. So what you're seeing is, this side, you're seeing currents going this way, coupling into the region 1, into the Earth, across the Earth, coupling out, and then back again. Okay? That's how that current system works. And then we can do the same thing on the southern side. But remember, patterns change, right? So again, it's the same kind of crosstail current. Hopefully I can draw this because I'm doing symmetry here. I'm invoking symmetry. And we've got arrows. Here, I'll do this. Whoop, that's a terrible arrow. So see how that is kind of like the magnetopause, the way the magnetopause current is, except instead of closing through that red, through this crosstail current, which also flows this direction. Whoops, I had red, what the heck? Give me red. Right? It closes that direction. These close that same direction too. But now they're being diverted into the Earth's upper atmosphere, which of course is shifted, sadly, because I don't know where the Earth's upper atmosphere is. It's supposed to be here. Hopefully that's close enough. That's what it looks like on my pad. So hopefully that makes sense. Anybody not understand that? Apart from my witty comments, this is very good. My witty comments are yours. How about my really stellar drawing? I could be Hunter Biden with this. This is so good. Should I sell this? Maybe I could sell it to a Russian oligarch for I'm just teasing. Who cares? Oh gosh. Okay. I think the dog thing has thrown me off completely. I'll never be the same. So now that I completely made a fool of myself, drawing this, but hopefully you understand that really when you divert some of this energy that comes from the solar wind, you can have it go across, right across the equatorial region in this cross, but you can also then divert some of it absolutely into the upper atmosphere of the Earth, both in the north and the south. And it doesn't necessarily mean that there has to be a space weather event for that to happen. And I know I've kind of trained you to some degree to believe that it always has to be that slingshot, and that's the only thing that shoots particles in. But no, it's not, right? As you're seeing very clearly, these currents exist anyway, right? They're just much weaker because they don't have a lot of flux to them. When you get that slingshot adding that much more flux to the picture, then you get much more, obviously, much stronger aurora. And it tells you why the aurora is so much stronger on the night side, right? You do have aurora on the day side. You do. It's diffuse, what we call diffuse aurora. Typically, you can't see it on the day side because it's not as bright as the sky, as the sun, right? So you never really see it. It's just the same thing as that you never really see air glow for the same reason. It's too dim. Well, you have air glow all the time, right? Even on the day side. But actually, as a matter of fact, you have more air glow on the day side because the sun is lighting up the atmosphere, and the atmosphere is re-emitting that stuff out all the time. So the only time you actually see it is with long exposures or in space with cameras that are capable of seeing it. But even that at night, the air glow is much weaker because it's still just re-emitting the stuff that it got from the day side, and it's slowly emitting. So in actuality, the air glow is actually stronger on the day side. It's just you can't see it because it's blinded by the light. Same thing with aurora. You have aurora on the day side and the night side, even when there's nothing going on. But when you have a solar storm hitting and you have that slingshot effect, well, then that finally makes that aurora super bright. And it also helps take this auroral oval that is typically at only high latitudes and really drops it down into mid latitudes. So then the Goldilocks zone, right, the mid latitudes gets affected. So hopefully that helps, at least with region 1 currents. Make an NFT of it. Oh gosh, no thank you. I've heard NFTs are like a total mess. I'm going to hang on to that for just a second and actually make a new note so that I'll clear the screen, but I'll hang on to that one just in case we want to go back to it. Okay, let's see. So Jerry, you say, so does this mean the region 1 and region 2 currents don't penetrate into the Earth and come out the other end? Oh, right. No, that's the magnetic field that does that. It looks like they deflected out from the drawing. I've been trying to figure this out. No, magnetic field and currents are totally different. Magnetic field are the ones that penetrate. Okay. Currents will not. They have a tendency to travel on the surface. Right, and that's the whole concept of like a conductor. If you're ever familiar with like a metal conductor, metal conductors, you'll never have electric currents and the electric field on the inside. You're safe from it. That's why people build Faraday cages, for example, because on a conductor, all of the charges will rearrange themselves. All the charged particles will rearrange themselves so as to null out that field. And currents will always flow on the surface of a conductor, but never inside. And that's the thing about electric currents, is that they won't penetrate. Magnetic fields, on the other hand, have to. And these are some of the differences between electric fields and magnetic fields are like the left hand, right hand, and they're always working together, but they are different. For instance, magnetic fields are what we call divergenceless. They're never a sink or a source in of themselves. If there is a sink, or if there is a source of magnetic field, then there must be a sink. We call it no magnetic monopoles, for those of you who are familiar with it. If you have magnetic fields that come out of something, they have to then sink into something else so that they can then return. And so they have this connection. That's why when you see the simplest magnet is a bar magnet. It has a north and a south pole. You'll always have 2 poles. You'll never have a single pole. Whereas with a charge, okay, an electric field, you can have that. You can have a point charge, for example. So that would be the analogous to having a north pole, but no south pole. You can't do that with magnetic fields, but you can do that with electric fields. So from that perspective, when you have, a North Pole and a South Pole of the Earth, you will have that magnetic field penetrate to the inside. But that doesn't, when it comes to the electric fields, they don't penetrate nearly so deeply. And so you won't have them go through the Earth, have the currents go into the Earth and then come out the other side. That's for magnetic field lines. And I don't want to get too complicated because I'm thinking I could explain a bit more, but if I do that, I think it's going to be it might get us in the weeds and get us locked into something else, and I don't want to complicate this any more than it has to be. Hopefully that helps, Jerry. But you and I can chat about this stuff off. That was from Wild Outcome with Spirit. Okay, good, got it. So hopefully, yeah, Spirit, let me know if that helps answer the question. If not, then ping me again or ping Jerry again. And like I said, if Jerry and Mike both know if you ask a bunch of questions and I'm not responding and you keep asking that same question again, they'll elevate it just like you just saw there. So I appreciate that, Jerry. I appreciate you doing that for her. Yeah, electrons travel on the surface, surfing. Exactly. Okay. Bar magnet, paper, and iron powder, right? That lets you see where the magnetic field lines are. Oh, you would. Oh, good. Okay, good. It makes sense to you. Fantastic. Yeah, it's, don't feel badly. Magnetic fields and electric fields are incredibly tough, and they're very non-intuitive because you don't see them, right? We don't deal with them every day. We deal with their forces every day, right? We deal with that every day, but we sure don't have an intuitive feel for how they work. And that's probably because we don't see electric and magnetic field lines. I think if we did see them, we would they would start feeling more intuitive to us. We'd understand them a lot better. Because I don't think inherently they're non-intuitive. It's just how we display them, how they manage to reveal themselves. That is how it's non-intuitive. So, okay. Oh, good. I'm so glad it was crystal clear. Okay. Is that the same as a what line? As a ley line? Is that spelled correctly? Ley line? Oh, ouch. If it is, I have no idea. What's a ley line? What is that? Sorry, I don't know. If you can explain what a ley line is to me, then I might be able to tell you the answer if they're the same. And Alan, you know a bit about magnetic field. Good. Yeah. So guys, tell me if I need to slow down or take time to explain this stuff better. I don't want anybody to feel lost. Okay. So for the moment, I'm going to go back to this diagram because now you understand the region 1 currents. That's the blue. Okay, and here in this diagram, they're showing closed field lines. So don't mistake this, this field line for a current. It's not. What they're trying to show you is that if you notice the current, the field line in black is very similar to region 1 and region 2. Region 2 is in pink. Okay, and the reason for that is because they're field-aligned current systems. Right? These are actually tracing along magnetic field lines. It's just that this is at the highest L shell, and you know that because it couples to the magnetopause, the edge of the Earth's magnetic system. And these are inside. Region 2 are at lower L shells because A, they're at lower latitudes, as you can see here when you map it to the Earth, and B, they're inside, right? They're not at the edge. Okay. Lower L shells, right, are closer and closer to Earth. Higher L shells are further and further away until you get to the last L shell, which is the edge of the Earth's magnetopause and magnetic system. Okay, so you got the whole idea with region 1. Region 2 is going to be easy. It's the same thing, just the opposite direction. Notice region 2s go the opposite direction. They come in, go across Earth and out. Not so far out, but then they close in the ring current, right? You remember from here, the ring current is exactly the same as the crosstail current, except it's in a ring. But it's co-located in the sense that it's in the equatorial plane. Okay, and really, for those of you who've taken the M series, you might recall what is the ring current essentially? Well, the bulk of it I gotta be careful when I say the bulk, because it's the bulk of what do you want to call the bulk? It's electrons and ions that are traveling. Remember, here's the Earth, right? They're traveling inside this tokamak, this accelerator, but they're not just going straight around and around and around inside this ring. Okay, they're not just going straight around and around and around. They're particles, right? And the particles are bouncing. They're gyrating around the Earth's magnetic field, right? And they're bouncing, and they're drifting. The 380 batic invariance. So this current is an average because the particles are actually going woo, and they're going around like this, right? If they're electrons, they're going around this way, and if they're ions, they're going around this way. Okay. Of course, currents are showing. They're showing the current direction is the direction of ions because that's standard. It's the direction positive particles flow, which is so ridiculous because electrons are the motorcycles, right? They move much more readily, and so most current is electron driven. But convention dictates that we look at the positive particle and dictate, and say that's the direction the current flows, what direction the positive particles flow. Ions flow opposite of electrons. So current system is shown with its purple arrow this way. Okay. But notice that's in the plane as the same as a crosstail current. Okay. So when you look at, if I were to draw, do you guys trust me to draw again? I don't know. Do I trust myself? I don't know. Let's see if I can find Earth. Earth is over this way. Yes. Okay. So there's Earth. And a little bit more. Let's draw like this. No, terrible. That's just awful. Oh, people. Yeah, it's the mirror that's really getting me. I am really messed up by this mirror. Yeah. Okay. If it were not, no, I won't do it quite that high. If it were not the mirror, I think I'd do a lot better. So if anybody knows how to do this with the YouTube thing without the mirror, let me know. All right, and then it closes again. So in this case, we have current flowing this way through the field aligned part. Then this may be too small for me to do an arrow there. I'm not going to do an arrow there. That's messy. But you can imagine what direction the current flows across in the Earth's magnetic system. And then, oh, right. And then, hang on. I think I've done something wrong. Erase. Did I do that wrong? This flow, yes, I did. Again, it's the mirror, guys. It's the mirror. Ugh. I promise to get better at this. I do promise. But I have to try it once. I have to start learning. I mean, it's the only way I can learn. And you guys do know that you are the baseline point of departure for lots of things for me. Right? You YouTube guinea pigs, you. So you get to see me at my best and at my worst. Okay, so hopefully you saw that. So, and tell me, is this instructive? Even with me flubbing around, when I'm drawing this stuff in real time, you actually see how the process works. And so this is kind of a smaller version of what we had before, right? Where you've got these currents going out, and I think they're going out this way. No, they're going out. I got to look at my pad. They're going out like this, right? Did I do that right? Did. Yeah. So they're going out like this, and then closing back this way. Okay. So again, it's the crosstail current in a sense, right? If I do a different color, I'll do green, right? We did green before. So the crosstail current comes this way. Right? So it's not very different. And again, in the southern hemisphere, you have that magnetopole. Oops, I should do that a different color, shouldn't I? I should do that back to, well, I don't want to do it red. I'll just keep it. No, I'll make it blue. you have the magnetopause current going like this. Whoops, it's not doing that. It's going the opposite direction, if I recall. Like that. Yes. And then in the northern hemisphere, it has to go this way. That's a terrible arrow. Right? Oh, God, that looks awful. So if I can do the line once better again. There we go. That still looks terrible, but. So again, and this is now just with region 2 currents. So I'm not really showing region 1 currents now. I'm kind of clipping through them. But do you see how it kind of does the same thing? In this case, however, right, you're still going the same direction as the crosstail current. But in region 2, it's the opposite of the region 1. And why is that? Well, because region 1 currents are closing up here. Region 2 currents are closing the ring crosstail current. Okay. And so if the region 2 are only closing through the crosstail current, they have to close in such a fashion that is consistent with that crosstail current, which means they have to flow this way. Region 1 currents are closing up here, which is have a current going the opposite direction as the crosstail current, which means they go the opposite direction. Anybody like over mind blown, kind of like, oh God, I can't take any more? Anybody overwhelmed? Oh. On settings, yeah, are there YouTube settings? Because if I invert the image on settings, then all the words will be backwards. See, then I can't do that. So I've got to have the camera going to YouTube being straight, right? It has to be straight form. I just want YouTube not to invert my image. So I have to figure out how to make that happen, because it really is frustrating for me to have to look in a mirror and try to do this as a mirror, because I don't teach that way. Yeah, I know. I'm a one-woman show, guys, so it's only me. So do you guys understand this with the region 2 currents now and the region 1 currents, that if we actually look at them in such a fashion, and I'm not going to erase that. I'm going to make a new note so that we don't lose it. So if I have to go back to those to either region 1 or region 2, I can show you those horrible diagrams I just drew. But if I've had a lot of people ask me, well, why are region 1 and region 2 currents, why do they flow in opposite directions? Okay, so you can see region 1 currents come this way from dusk to dawn, right? Because this is dusk over here. This is dawn over here. And then region 2 go from dawn to dusk. Okay, because this is dawn over here and this is dusk over here, right? Midnight is right here in the middle, right? So if you're looking down at the Earth from the North Pole, right, and you'd see a clock face. Noon is behind us, is the other side. Midnight is pointing out at us, right? We're at midnight. 6 a.m. is over here. That's dawn. 1800 would be here, right? That's dusk. Got it? We got it. Do these diagrams help me drawing stuff? Does that help, or is it just hilarity? Just comic relief? The boffins are baffled. Oh no, don't tell me people are baffled. I don't want to hear that. So it looks like a lot of people have got it. A lot of people are understanding. So what segregates region 1 from region 2? What's the mechanism that generates the region 2 current? Ring current. And also a need to relieve some of the stuff going on in region 1. And we'll talk about this in a sec, okay? Oh, good, they do help. Yes, it helps. Oh, good. Good. Oh, that's great. Everybody's saying it helps a lot. So you're willing to put up with my ridiculous ability to draw right now and all the issues I have with mirroring images because they help. Oh, good. Excellent. And Jerry, you say that too? It helps because I need you to draw me a picture. Oh, I'm so glad. Putting a ring on it. That's cute. Yeah, we have Beyonce sing. Have her do a cover. That's what we should have. We should find songs that, like pop songs, that have some type of space weather component and than do parody music videos and just have it be all. Should take clips. Anybody want to do that? Take clips from my mini courses and just have it be like the Beyonce song or something. It'd be hilarious. I wouldn't even care if YouTube put an ads on it because it'd be so funny. Oh, anyway, okay, it's just nice humor with science. Good. Drawing is good. Oh, good. Okay. A Weird Al cover. Yeah. I have to rewrite the lyrics. No, I should get Ward Silver to do that with his oh God, what was the name of his band? Is it Nocturnal Emissions? Oh God, I forget what the name of his band is. Something that ridiculous. Anyway, okay. So hopefully this helps you understand. And again, we could get even deeper when we start talking about Pedersen currents. I mean, Pedersen and Hall currents. Notice that what they've done is they've taken it just here in this case from the southern hemisphere, just this tiny thing here, and they've blown it up, right, just the bottom edge of the Earth. And they're showing, once again, remember, currents flow on the surface, right? So they're talking about in the upper atmosphere, and they're showing because region 2 currents come in, you're going to have a Pedersen current going this way, and it can actually, in a sense, it's consistent with region 1. So you can have region 1 currents coming in, driving Pedersen currents this way, and then that also helps drive region 2 currents out. There's always consistency. You've always got to be consistent because that's what happens with particles in that are charged, right? They're going to flow whatever way the forces are. And so if region 2 is driving something in here and you've got region 1 driving out here, you're going to naturally end up having other forces on the particles down below that will drive them this direction to feed this current. Okay. And the same thing, you'll have, if currents are coming in, you're going to end up having region 2 currents coming out. You're going to have particles being driven from region 1 to region 2 so that you're feeding that current system going out. And everything that is done here in these Pedersen currents and in the Hall currents that are associated, these are mainly ions, but the Hall currents are mainly electrons, and they go perpendicular to this. But we'll talk about them a little bit. All of that stuff helps exhaust the energy that we're getting pumped into us from, remember the sun, remember the solar wind, right? So all of this is this wonderful ballet that's ensuing. And it's communication from the Earth, from the solar wind to the Earth's magnetic system, and then it couples down in here, and it's finally blown off. The energy is finally exhausted, what we call joule dissipation, in through the upper atmosphere. And there's even more to it than that. And I might even talk about the flywheel, the fact that the Earth's rotation and the particles and the convection patterns that are set up in the charged particles also ends up setting up convection patterns a little bit in the neutral winds as well. And those, depending upon how long a solar storm lasts, for example, these patterns spin up the Earth's upper atmosphere, literally spin it up. And as it spins it up, then when the source is taken away and all of this dies, you still have this flywheel, this stuff spinning, and it takes a while for it to slow down, right? So when you have a solar storm going on and then suddenly the field turns northward and all of it turns off, it's not a light switch, not at all. It goes, okay, kind of takes a while for it to calm down. That's why you can see after a big G3 level storm, it goes northward. People for hours are still seeing aurora, but the aurora is looking weird. It's looking like puffy, a little cloudy, kind of like diffuse, fuzzy stuff, softer, right? Velvety. I don't know, that's a technical term. And it lasts like that, almost like it's dissipating like a mist, like it becomes like an aurora mist. That's that flywheel spinning down. The energy that's already built up, the inertia in a sense. Yeah, I guess it is really inertia that's built up. Those currents will still flow because it's been spinning for so long, it can't just shut off, right? Because these are actually, it actually causes particles to actually spin, actually move, actually convect. And we'll talk about that in a minute, probably pretty quickly. Okay, so an overview again. Current systems get complicated really fast, but oh my goodness, you actually now, and I showed this to you guys ages ago, and I said, don't worry, this is like incredibly complicated. But if you actually took a time, you might actually be able to understand this now better than you've ever understood it. So when we look at here, for instance, we'll start with this little guy, okay? That blue, right, you should recognize it. That blue is just the region 1 current system. It's being blown in, down here, right? You've got the field aligned parts, but then it also closes up here at the edge of the magnetopause, right? And all the little grayish lines, that's just showing magnetic field lines, trying to show you the Earth's magnetic shield and the way it looks, right? You've got the dipolar parts out here. I'm just looking at the gray lines. The dipolar parts out here, that's that slinky. Okay, you can kind of see them, right? See them all looped in, all closed, like a distorted slinky. And then back here, all this stuff, this is actually being pulled back. This is part of that slingshot, right? So you've got magnetic field lines. You can even see some closed field lines that are really distorted. That slinky really being pulled back. Do you see those? You can actually see those closed magnetic field lines that look like slingshots being stretched, right? And so then you've got these currents, the closing currents up in the northern hemisphere. And of course, in the south, if they drew it, they'd have the same thing, right? And you can even see where the crosstail current would be, right? So the blue is not hard to think of. That's region 1. And then here, they're showing region 2. Inside of the magnetopause, you're seeing currents being pulled in this way. And again, going into the Earth's upper atmosphere, coming out the other side, and they're connecting in the pink, which is that ring current, or this way. Am I doing it the right way? This way. Here's that mirror problem again. And that's that pink line. So even in this diagram, this is all the stuff that we went over. Right? Jumping over here, now you've got dusk on this side. You've got dawn over here, right? This is showing the equatorial plane, right, where the equator of the Earth is. You can even see the equator shown in a dashed line, right? Okay, so you're looking kind of obliquely down onto the Earth's upper atmosphere. The sun is off, whoops, the sun is off this way, out here somewhere. Why do I say that? Because midnight's right here. See midnight, and it's pointing, boop, right there. So there's midnight. So this whole backside, far side of the Earth. I've never had to say that. Night side of the Earth, let's say that. This is all night side of the Earth, okay? And dusk is right here. There's 1800 hours right here. 600 hours is right here, okay? So noon is, again, out here. The that brown ring is sitting in the ecliptic plane. That's the ring current. Okay, that's the normal ring current. Notice that there are other lines that get lined up in here. Okay, and I guess I could talk about them right now. The green is essentially the region 2 currents. Okay, and it's showing it closing in the ring current. Okay, so you're seeing that ring current closure, and you're seeing it pop in here. And then it goes across. You're not seeing it going across. And there's other stuff in here. You'll see that in a second. Right? And now what you're seeing here, and they've done this on purpose, I think, to separate out the magnetopause current, making it look like the magnetopause current actually has a bit more to go. There really isn't much of a distance between the magnetopause current and the region 1 currents, which you're seeing here, but they just wanted to make the magnetopause current look, distinctive. And here's the region 1 current. So in this case, this diagram is really looking at the region 1, region 2 currents, coloring them both green as if they were part of the same system. Because to a great degree they are, right? They're the aurora system. As I draw it out, okay. But remember, the region 1 currents close in the magnetopause with the magenta. Region 2 currents close with the brown, with the ring current. Okay. Now, you notice that those aren't the only lines in this diagram. There's a little bit more. Down here is the crosstail current. They just call it the tail current. Believe it or not, you can get disruption in the crosstail current. Okay, we call this a substorm current wedge. Anybody, and Adrian, if you happen to be watching, anybody who is familiar, who's at high latitudes, and any amateur radio operator who's at high latitudes has had to deal with substorms. Substorms are a slingshot, right? We're used to that slingshot, slingshotting particles from the tail. But, and actually I have to do it this way, slingshotting particles from the tail, okay? But not to the, it's not as dramatic as, let's say, a big geomagnetic storm. So when we have a big solar storm hitting Earth and it's just rattling everything and it's a G3, la, 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 la. Okay, that is like this system gone amok. It's the whole tail goes. The whole tail becomes a slingshot. And if there's any scientists watching, forgive me, I know that's not exactly right, but it's right. And it simplifies it enough before we get into too much argument about what reconnection really is and how it occurs, because that's a whole nother ball of wax. As a matter of fact, you can get a PhD in reconnection and the different types of processes that occur and how it occurs. But reconnection has a tendency to be very patchy, which is partly probably why you're allowed to have substorms and not just have the whole thing go. So in a substorm, really, and there's a lot of arguments as to whether or not substorms are actually driven by solar wind stuff or if it's just an internal reconfiguration. Likely it's both. Sometimes the Earth's magnetic shield is just not quite happy with itself and it needs to reconfigure. So it reconfigures itself and it can start a substorm in of itself without any solar wind prompting. Okay, you know, sometimes you just need to do spring cleaning, right? May not even be spring, who knows? But substorms oftentimes can happen just in of themselves, and that's when the Earth decides it needs to quote unquote dipolarize part of itself, which means it will stretch that slingshot and let it go on itself to bring the field back into a more dipolar configuration, and it shoots particles. So you will get currents. So you will get these little tiny, kind of like pseudo region 1, region 2 current systems going. Okay, but they're localized, and so we call that the substorm current wedge. Okay, and that's what you're looking at here. And yes, it's always tailward, right? Because it's always the tail that is doing it. Whether it's a big geomagnetic storm or a small little substorm, you're always talking about pulling part of that magnetic field back at the Earth that's close field lines and shooting things forward. Okay, reconnecting and shooting things forward. And that's what you get here. So that can add to things. And especially when you don't have a geomagnetic storm going, you can have, this is part of the reason, this system here is the reason why you can have aurora at high latitudes going gangbusters and mid latitudes going, I don't see nothing, right? Part of it can be that because you can have these substorm current wedges when the auroral oval is really tiny and you can light up the high latitudes really well. And then you also get another system called the partial ring current. And again, it's like another region 1, region 2 kind of thing, or region 2 kind of thing going on, but it only happens in a small section, typically dusk. Okay, a lot more electrons at dusk than, well, I don't want to say that. I gotta be careful because when we get them shot, they actually move dawnward. So I gotta be careful when I say that. But you can get a partial ring current that typically happens more often at dusk. I'm not even sure if we get a partial ring current at dawn. But as you can see from this, the ring current is oftentimes much thicker, much heavier, much denser in the tail than it is on the day side. Okay, and that is multifold. It's partly because region 2 currents close in the tail. The substorm current wedge closes in the tail, and you have the tail current. You don't have a lot of that in the front. In the front, you have the magnetopause current at the edge. You don't have a tail current feeding it. So anybody who thinks that the ring current, that brown line, is just even all the way around. It isn't. Okay. Anybody not understand this diagram, at least to the level that I've explained it? Wow, I see lots of stuff in the, oh my goodness, okay. I'm reading. Semi-esoteric terrestrial, okay. Are we talking about, sounds like there's metaphysical conversations going on at the same time, which is fine. I don't have a problem with them. Sometimes, yeah, okay, oh yeah, you guys are talking about physiological issues. Yeah, the thing is, with these current systems, remember, they're very tiny. And really, for most people who have physiological impacts, it's not going to be directly from these current systems. It's going to be more from bigger storms and from the Earth's magnetic shield. So these gray lines out here wiggling, okay? And the wiggling of those gray lines, those magnetic field lines, because they're anchored in the Earth, are actually going to drive and induce currents in the ground itself. And those are the currents that you're sensing. You're not necessarily sensing these currents that are way out here in space. That's not nearly as big a deal to you. Those currents are a bigger deal for spacecraft than for people on Earth. People on Earth are more concerned about either cosmic ray flux if you're in an airplane, or and solar radiation storms, or you're dealing with geomagnetically induced currents on the ground and the wiggling of the magnetic field. Okay, which is more ground effect, and we'll talk more about those. So we'll talk about things when we get to the ground level effects, because we're still up in the atmosphere, right? We're talking about those effects, and that a lot of that stuff that affects the ionosphere is really beginning in space, right, in near Earth space, has its origins there. But when you're a person on the ground, really what you're dealing with are things like pulsations, okay, PI pulsations. No, I'm not going into Schumann resonances, because those are from the neutral atmosphere, and I'm not going to go into a lot of neutral atmosphere stuff. But there are lots of electromagnetic sources and that drive currents that can cause sensitivities in people. So that's really what, when you're physiologically susceptible, it's not so much this stuff, but more the stuff that gets induced in the ground. Okay, but we will talk about that in probably another 1 or 2 courses from now. I still don't understand how people can forecast weather, terrestrial weather. I don't think people can forecast terrestrial weather from that, but I do think that people can look at storms that are already occurring and see that there is going to be coupling into terrestrial phenomena. And the more research that is being done on this, the more consistency and repeatability people are finding from studies. And they're also finding mechanistic connections. So for instance, I was talking just the other day, maybe to my Patreon crew, I can't remember, but I was talking to my Millersville students about some of the coupling that they're seeing between terrestrial events and weather issues in the neutral atmosphere. How one of the main ways it seems that they're being coupled to the electromagnetic, the upper atmosphere stuff, is through gravity waves. And gravity waves take a finite time to reach the upper atmosphere, so the ionospheric layers. And that time constant, to the period of time it takes for it to reach that distance, is very consistent with things that we're seeing, with changes in either the density in the charged layers, or things that we're seeing in the terrestrial environment. So, we're even seeing sprites and jets that are occurring at the right time that it takes, at the amount of time that it takes let's say a hurricane to propagate gravity waves up to the E layer. And I was talking about this just the other day. And at the time it takes for that to happen, we'll see a sprite go. Okay, we'll see a blue jet. That is coupling literally, and you'd think it's just going upward, but what's also happening is that we're seeing the sporadic E layer, for example, draining all of its charge into the neutral regime and into the cloud, into the hurricane, let's say, and it actually then intensifies the lightning, because what's happening is that those gravity waves are facilitating charge exchange. They're dropping the threshold for an arc to occur. Right, and the sprites and jets are part of that process. Really neat stuff that we're beginning to elucidate. And more and more people in mainstream science are beginning to pick it up, which is really cool. It's not necessarily just a fringe science thing anymore, but we do need terrestrial meteorologists and space weather physicists to work together on that to be able to solve that problem. And you'll see a little bit more of that as we continue diving a little bit deeper into this. So yes, you can, to some degree. You can't necessarily say what the weather is going to be like, but you can possibly say that there are phenomena that are being intensified, or there is a bigger chance of winds picking up, or lightning becoming a bigger issue. More lightning strikes or more intense lightning strikes because of certain space weather phenomena. And another source of that is intense cosmic rays or radiation storms, and that is being borne out in where you see lightning occurring on the planet, where the most lightning strikes occur on the planet, just at any time, is, believe it or not, in a place on a lake in South America, very close to where the South Atlantic anomaly is. And the reason for that, very much likely, is due to the fact that you've got a higher concentration of particles penetrating. You're in there, energetic particles penetrating. And it's helping. There's lots of cosmic ray showers in that region, and you've got a lot more charge buildup in that region. So that then facilitates, as that stuff drains out into the neutral atmosphere, it allows for lightning to be more intense and more frequent in that region. So we'll see a lot more of those types of studies come up probably in the next decade. I think we're beginning to really make headway in that regard. Okay, so hopefully it looks like people are understanding this. Can you talk more about gravity waves? A little bit, not much, because that's a totally different topic, and I don't want to get too far off topic of this, because I mean this has already been a very long class, and I've barely gotten through anything. But yeah, I can bring that up as time goes on. Okay. Do solar flares damage solar panels? Not solar flares. No, solar flares won't damage a solar panel. Are you talking about on the ground or in space? No, that's not an issue, and not even solar storms do that. Our atmosphere protects us from a lot of that stuff, and then solar storms, of course, the solar panels are too small to induce large currents in. Even geomagnetically induced currents are too small. You have to have power stations. You have to have, if your solar panel were the size of Lake Michigan, then yeah, possibly, but they're not, obviously. So it's not going to be a problem for you. I'm not putting you on the spot. I wouldn't talk about them on our channel either. No prob. Oh goodness, I don't know. That sounds like a conversation with other people. Do less sunspots explain our winters? Oh boy, that's climate change, right? Yeah, let's save that for another discussion. I actually went over that in great detail, I think, when I did my class on the breathing heliosphere. So if you want to check out that class, because we talk about pseudocycles, and we talk about big grand solar minimums and big grand solar maxima, and the level at which that might actually play in the role it plays in climate change. I think we have not begun to understand the level of change that the sun can go through, because there's been lots of minimums and maxima that are much lower and much higher than anything we've seen in the space age. And can that kind of thing happen if it happens over a long period of time? Yeah, possibly. Yeah, I think it's very, very, very plausible. But again, we don't even understand the coupling very well between the sun and space weather to the neutral atmosphere and terrestrial weather. And so a lot of those questions are very difficult to answer as of yet. And I think there's going to be controversy for quite a bit of time to come on that particular subject, and how it relates to anthropomorphic or anthropogenic effects. Whew, boy, that's above my pay grade. I'm not even going to go there, because I'm not an economist, and I also don't study, how this stuff affects the neutral atmosphere and fossil fuel burning and all that kind of thing. That's just crazy. Really hard to unpack. very too many variables, to be honest. Okay, so hopefully I can move away from this. And what I think I'll do is as we go into Pedersen and Hall currents, I might go back. You know what? Yeah, I think that's what I'm going to do. All right, let me go over this just a little bit, and then what I'm going to do is I'm going to jump into how these current systems, as we're beginning to learn them, can actually change in high latitude regions, which is what I really wanted to talk about, especially for amateur radio operators, because it's so critical that you guys realize how important it is to look at space weather magnetic field, coming in, the solar wind magnetic field as it comes in, because it really does change stuff. So I'm going to no, let me do this side. I'll do this side first, simply because this is the picture that you guys are used to seeing. So when we zoom in, right, at this point, we're zooming into Earth, no longer looking at how they close out in the Earth's magnetic system. We're just going to zoom into the locale, the region up at high latitudes. Hopefully this diagram makes sense to you. You see the region 2 currents coming in at lower latitudes. Remember, they're coming in from the ring current, so they're going to be at lower latitudes, lower L shell. You have a current that then brings them up to the region 1 currents. The region 1 current comes out. Remember, it's going to go out and connect to the magnetopause current, right, the very outer edge of our Earth's magnetic system. So they're at the highest L shell, right? And they're essentially sitting at where the boundary between closed magnetic field lines and open ones. Any magnetic field line from the Earth that's coming out in this region is open to the solar wind. Okay, so particles are raining down from the solar wind here in this open region. So obviously, if there was a radiation storm, this whole region would be lit up like a Christmas tree. But we're not going to talk about radiation storms right now. So here's the other edge of that region 1 current coming in. Here is the Pedersen current. This is the ones that are mainly ions closing straight across and then going out. There is another set, and so that's easy to understand. And of course, Pedersen currents again go from the region 1 currents on this side to the region 2 currents straight across, and then so the region 2 currents go out and close in the ring current. There is, even though this is reasonably straightforward, you can just draw a straight line from one edge to the other. And by the way, this is the day side. So you're coming out. So if you wonder why is it backwards from the diagram you just saw, why are the arrows pointing backwards? It's because we're now looking at we're looking at Earth from the day side. We're looking at it from essentially the sun's perspective, instead of looking at it from the night side, which is through this diagram to the other, behind it. Okay. But in this case, when we look at Pedersen currents, they draw straight lines from region, the two sides of the region 1 currents. But then we get to the Hall effect. And the Hall effect, it's a little bit more complicated and non-intuitive, and it has to do with E cross B. It has to do with electric field and magnetic field. And when you have this, you can actually get currents that are being driven perpendicular to both the electric field that's already being created and perpendicular to the magnetic field, right? Magnetic field is pointing straight out. So that's how you get the Hall currents. And Hall currents are essentially electrons. And that's why they are circular, because they have to be perpendicular, right, to the Pedersen currents. As you can see, this line is perpendicular to this line. Oh boy. Okay, right? Perpendicular means, like this, right? And it's also perpendicular to the magnetic field, which these are, the magnetic field is pointing out like this, because this is the field-aligned current system, right? So these currents are directed exactly the same direction that magnetic field is pointing. So the Hall currents, which are these circles, okay, are perpendicular to both the electric field and the magnetic field. Complicated, I know. But what it means is that electrons are moving around in circles, kind of, circling the wagon, so to speak, right? When you're looking at the region 1 current things. And if you can see, there's 2 sets, right? There's this set that's circling this loop, or this, pole, this stake, as I stake the currents to the earth, you've got this one that's circling this loop, and then you've got this one over here, which you can't see quite as easily, and it's circling the other way. Right, if I did it, and I'll show you a Comet MedEd module that shows that. Okay, so hopefully that makes sense when you look at that. And this current process, so if you look at it from this perspective, and I think the MedEd module will show it more closely. The interesting thing is that means electrons are moving toward the dawn, or toward the day side, toward local noon out here. Because you see the arrows, they point out like this. Do I need to draw? Because you say drawing helps, so let's see. Okay, I'm trying to mirror myself. Where am I? It's too far. And it'll be here. Let me. Nope. See, mirror. Here's a problem. Okay, so let me think about it like this. No, that's this way. Yeah. Okay, so it has to be that kind of line, and then around. All right. Let me erase all this stuff. Erase. Okay. So currents are drawing this way. Okay, near 12. If this is noon, 12p. Local. I'm like, did you see that backwards? I see it backwards. Huh? You guys don't. Okay, so that's that. Now, what you get then is that you get currents that are doing this. Let's see if that works. Yes. Good enough. And then a current system that's going like this. And they're all pushing forward, right? So that whole thing right up the middle, this way, right up the middle is pushing this forward. Those are electrons. And then they just circle around. And the same thing on the other side. They circle around. Okay. So obviously this needs to be on the planet, not above it. But they're encasing the region 1. Okay, the region 1 currents that are coming out. Okay, same thing. Encasing the region 1 currents that are coming, in this case over here, they're coming in. In this case over here, they're coming out. Okay, so it means they're flowing in opposite directions, which they are. One is circulating in a clockwise fashion. That's probably for you because it's backwards for me. So that's probably the clockwise one for you, I hope. Because for me, it's counterclockwise, but I'm mirrored. So I'm assuming that this is the clockwise one for you. And then this one will be the counterclockwise one. Okay, but that makes sense because, again, the currents, region 1, come in on this side. They go out on that side. So the currents have to be reversed. But what that does mean, again, is that there's this net flow of electrons toward noon. And then there's a net at lower latitudes. Right, there's a net flow of let me be careful. There's a net flow of electrons moving toward noon at very high latitudes, right over the poles. Okay, magnetic poles. And then at lower latitudes, they move duskward. The currents do. See that? Sets up circulations, right? Begins to set up circulations of, because you're creating these currents all cause anything that's charged to recognize it and move around because of it, right? Not the neutrals. The neutrals don't care, but the charged particles do. They see this and they must obey. This is a current. This means it's driving electric fields, which then drives magnetic fields, which then causes particles to move, right? And it's a self-perpetuating machine in that sense. So you have particles that are driving motion toward noon at high latitudes, toward dusk, or toward the night side, I should say, toward the night side at lower latitudes and around. Does that make sense to everybody? I'm gonna erase this. I'll make a new note. Whoop, not that. So I'm keeping that note. Okay, hopefully people understand that. All right, so how high above the Earth does this happen? It happens far enough out. I mean, the magnetic, I mean, the particles get pretty diffuse up here. So it'll continue to happen. But when you have less and less particles, you don't notice a current, right? So because particles drive current strength, right? The more particles you have, the more current strength you have. Then the particles continue to do this up, 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 up. But the problem is there's no current being driven because there's so few particles. And then if you have so few particles and the current is that weak, well, then no particles end up, they don't respond to it as much because there's not much of a current being driven. So it just kind of peters out as you get higher and higher in altitude, to the point where it's, the particles are so vacuous. I mean, the density is so far down that it's not really, you're not really seeing it anymore. And I'm not sure even where that is. I would think where you fly a spacecraft is probably about as far as you can, you could maybe even measure those current systems. I'm not even sure anybody's ever tried to measure the top of where these current systems live. That maybe that's already been done, and people, or scientists are pelting me with olives, going, "Tamitha, we know very well." And I don't know, because I'm not an ionospheric physicist. Just know that the upper part of the atmosphere, the ionosphere, actually goes out into the plasmasphere. I mean, it's really the upper extension of the plasmasphere, and so then different dynamics begin to take over, because now you've got to deal with the rotation of the Earth as well, which we'll talk a little bit about in a minute. But it's a very good question, and I'm sorry I don't have as robust an answer for you as I would like. Maybe it's something I'll look into a bit more later. But yeah, that's the limitation of an interplanetary physicist trying to teach you ionospheric physics. I just don't know it all. Wish I did. Wouldn't that be great? Okay, so again, here's another diagram. I don't think this diagram at this point teaches us anything. I've really gone over a lot of this stuff, but it just kind of highlights once again, some of the fact that these current systems really are kind of I don't want to say hodgepodge. They're not hodgepodge, but they really can be diagrammed as different parts and different pieces of different things, right? And how they all kind of interconnect together. And depending upon what diagram you're looking at, they will lump certain things together and color code things certain ways. So like here's yet a third way of color coding something, where you've got you don't even have region 1 and region 2 currents being color coded the same way. You have current systems going outward that are being color coded a certain way, right? No, this way, mirroring. Color coding, anything that moves out as red, right? And anything moving in, as you see here, moving in as blue, irrespective of whether it's region 1 or region 2. So there's lots of different ways to color code things depending upon how you're teaching the material. Don't get confused, right? There is no wrong way. But you do have to be incredibly meticulous when it comes to defining things and knowing the perspective through which, what lens are you looking at these current systems through in order to understand them. Now, yes, it can get extremely complicated, because remember, and I'm going to go after this, I'm going to go straight to the med-ed modules so we can really talk about them, and you can see nice animations that hopefully will kind of pull things together for you. But remember, they don't act, these current systems are not in a vacuum. Well, careful, space is a vacuum. So they don't work in isolation. It's not just about region 1, region 2 currents, right? There's all sorts of stuff, because then you can couple into the solar wind and the Chapman-Ferraro currents that sit on the front, right? You've got the current systems that are you've got the quiet current systems. Gosh, did I even talk about those yet? Hang on, folks. No, I haven't, so I got to be careful. I guess I'm talking about those when we hit to the ground. Whoops, what did I do? We'll talk more about these current systems, the solar quiet current system and the lunar quiet current system. I mean, there's a lot of different current systems that we still haven't even talked about. But know that there are currents at other in the upper atmosphere that are that are lower latitudes, that are driven by other things. Okay, so these are not the only currents that are being generated in the Earth's upper atmosphere. There are other ones, and yes, there's all this this coupling in from the Earth's magnetic system, gyrating in energetic particles, precipitating, all of that stuff, and all of that matters. And then of course you do have things, and we talked about gravity waves, but here's other types of convection um, causing this stuff here to actually propagate down to lower latitudes. And some of that becomes a meridional circulation flow because you actually have heating. Aurora heats things, right? Maybe mostly collisionless. Like if you were to touch aurora, you wouldn't get burned because there's really no radiation to it. Because the how do I explain this easily? The upper atmosphere is so vacuous that there's not enough particles to touch you and actually, deliver enough heat that they can get very, very hot. You can have very, very hot temperatures and you can stick your hand in it and not get burned because it just isn't enough. It's just not enough to affect you. The heat radiation level is so slow because there's so few particles that are actually touching you. Once you get to obviously higher densities of atmosphere and enough so that you can get heat transfer quickly, well, then yeah, you'll get burned. But in the vacuous area where the aurora occurs, heat transfer is so slow because there's just so few particles there. That you can be in a plasma that's 1,000,000 degrees and not know it. It'll feel ice cold for that reason. But that it's still, relatively speaking to other particles in the upper atmosphere, they know what's the story when it comes to temperature. And these temperatures will actually set up circulation patterns down to lower altitudes. And that's part of how the auroral electrojet gets going. Because the indices that occur, they're actually not in the auroral zones. The auroral electrojet, like the AE indices, are actually lower than that. So it's interesting when you get to this region, some of the dynamics that occur, and how that couples back into the Earth's magnetic field, and how that couples back into neutral atmosphere. Oh my goodness, it's just once again another aspect of this very complicated ballet that we're trying to scratch the surface of, as you can see very clearly. So I just wanted to make sure that you understood that there's so much other stuff going on. And all of this stuff up here propagates down to lower latitudes and then couples into the processes that are already occurring down there. Okay, so keep that in mind. But it also lets you know that why, when we talk about mid-latitudes being the Goldilocks zone, it's because most of this stuff stays up here. It's like what's in Vegas stays in Vegas. No, not quite. But, it takes a while to propagate down. And so this region oftentimes is very much a Goldilocks zone for those of us who live in, the lower 48, so to speak, or obviously in Europe and everywhere else. So what I'm going to do, because I think, let me go to the next slide. Yeah, because the next slide I start getting into indices a little bit. Let me take just a second though. Can you believe we've only gone through like 4 or 5 slides in this entire thing? Wow, we've gone through so few. But I think this is a really good, this is probably the most in-depth I have ever taught when it comes to current systems. And I think it's probably very smart that I've done this. So I don't recall what the rest of this video is. I've got a couple other videos I want to show you, but since we've been talking about Patterson and magnetospheric currents, let's just play this for a sec. So again, that's region 2, right? We can take a quiz. What is this? So now you saw this diagram. There are the Hall currents. There are the Patterson currents. Okay, now they've zoomed in on this. Boy, they do this fast. Let's stop for a sec. So what they've zoomed in on, if I back up just a smidge. Let me wait till they get to the stop. Okay, so what they're zooming in on here, right? They're just showing you, okay, we're about to zoom in on this plane, just the white stuff, right? You're so official. So they're just going to zoom in on a section of the Patterson current. So you're not going to see the region 1 and region 2 anymore. But you will probably see, I think in the diagram, you'll see the perpendicular part of that convection of the Hall currents. right? And if I need to draw on the diagram, I will again. But here's that stuff. Remember, this is now the day side, right? This is noon at very high latitudes. And so you're going to see the yellow lines cutting right through, probably going from north to south in the next diagram. And that's going to be part of the Hall currents. Okay, you're not going to see where they close as they go back to the night side on at lower latitudes. You're only going to see at high latitudes, super high latitudes, where they go. Yep, there we go. Okay, so here's the Pedersen currents, right? Because we're cut through that now. The magnetic field is shown in blue, right? And they're trying to show it by it being kind of oblique here. They're trying to show these are the magnetic field lines that are penetrating straight down into the Earth. So these are supposedly essentially vertical at this point. Okay, they diverge a little bit because remember they have to curve back around, right, in that slinky. But essentially in the northern regions they're vertical. So they're just these lines probably show it the best. They look probably the most vertical. Okay, so they're coming straight down. And you've got the Pedersen currents going across, right? And it's going from in region 1, was it? I forget. Does it go from dusk to dawn, I believe? Right? Correct me if I'm wrong. You guys know better than I do now. You should be veterans at this. And then, of course, it should be dusk to dawn, shouldn't it? I'm awful. I have to go check. It'll bother me and I won't be able to teach. No, it goes from dawn to dusk. I knew I had it wrong. So it goes from dawn to dusk. Because I was thinking, wait, I have it mirrored. Right. So it goes from dawn to dusk for region 1 and then back out. Glad I checked. It would have totally bothered me. Okay, so from dawn to dusk. Okay, and now you're seeing, that better be right, because you're supposed to be having the Hall currents, right, moving electrons in this direction, moving electrons from in high latitudes from the night side to the day side. Okay, and then of course you can actually see some of that returning for those Hall currents. And they're saying, if you're just curious about the words, the closing currents comprise both Hall and Pedersen. Pedersen currents flow parallel to the electric field and perpendicular to the magnetic field. So they're showing them. So that's why they're showing the Pedersen currents moving in the same direction as the electric field points, which we know the electric field is pointing the same direction as the region 1, region 2. And then, the region 1 currents. And then remember, the magnetic field is pointing straight down. So that's going to be perpendicular to the Pedersen currents, right? Because straight down, it's still, you point straight down and then you have this way, that is perpendicular, right? And then they say the Hall currents flow perpendicular to both fields. So if you have the electric field going this way and you have the magnetic field going this way, right, straight down, so you have them flowing, am I doing that right? Which way is the electric field in this diagram? This way. The only way you can get perpendicular is to have it going toward or away from you. Okay, and that's what they're showing in yellow. And let's see, what else does it have to show before I get into, to me, I'll show you the fun stuff is when it, so they're pointing the Hall currents out now. The fun stuff for me is when they, I think we're just going back out here. Hang on, what are they saying? Atmospheric conductivity or uniform. Oh, don't worry about that. I guess, no, I'm not going to talk about that. The fun part for me is going to be what I'm going to show next. I just wanted to see if there was anything else in that particular movie, which there really wasn't much. Okay, is this the cool one? I think this is the cool one. So let's see how far back it goes. So I want to show you the same thing. I don't know if I want to show you all this stuff. Play. Tangential stresses, we don't really want to talk about that. That's just too much detail. I'm waiting. There's a narrator, yakky talking, and I just, okay, fine. No, this is where I want to be. Okay, so this is where it gets interesting, guys. I'm wondering which side I should stand. So what we're about to see, okay, this is the solar wind coming in. This is a solar wind magnetic field pointing southward. Okay, so this is a normal storm condition. This, you're going to see this magnetic field, and this is similar to what I think I showed in the last class. I think I did a review for everybody for the first like few minutes because I was asked to do a review. So I decided to show the Comet modules, and it wasn't even a Comet module at the time. I just grabbed a video off of YouTube, which ends up being very similar to this one. So the magnetic field from the solar wind is coming southward, and it's going to couple against this, and hopefully you can tell, it's hard for me to see, but hopefully you can tell that's the Earth right there, right? And then this is the Earth's magnetic field. This is just one L shell, one slinky, one field line depicting an L shell, okay? And it's going to be essentially the L shell that reaches the edge of the magnetic system, okay? So this blue stuff out here, again, is the bow shock, and it's deflecting all of this plasma out here. That's the solar wind being diverted, shocked solar wind being diverted, which means it's not pristine solar wind, it's been altered so that it can divert around. The red line is the edge of the Earth's magnetic system. That is the magnetopause, right? So that has the magnetopause current, right? It's defining that cavity. And you'll see if they do the diagram right, they'll show this magnetic field line here reaching the edge of this. Because how else is it going to interact with that magnetic field coming in from the solar wind? But when they do that, you're going to see the system that's set up. And that's well, no, they're not going to zoom in on that. But you will see how this magnetic field line actually moves. And you'll see the slingshot. So, whoops, you know what? I think I should stand on this side because I want you to see the slingshot. That's the most important. Okay, so as it continues to play, there you go. Right? Let me pause it. Okay. So did you guys see that you recognize this, hopefully from the last class? And again, I can move it back just a smidge. Actually, does it move back? Oh, goodness gracious. Too far. Steps are too far. So there's the magnetic field coming in. And yeah, see that you're seeing that magnetic field line right there, the Earth's magnetic field line coming right up to the magnetopause. And of course, as this solar wind field line hits this, because this field line is southward and this field line is northward right here, you have north and south, right? Right? As soon as they touch, they annihilate each other. So what happens is that you get reconnection, and this snaps and breaks this field line. If I can move my hands in the right place, breaks the field line, and it will open it up, right? So you get that. That's my funky chicken dance, right? How many times do I have to do the funky chicken dance, right? It closes and then opens, right? And folds back, right? Right? Closed. And as soon as that field line hits, it breaks it open and begins to fold it back. And you'll watch that. Funky chicken dance. Right? There's the breaking, the opening, the beginning to fold it back. Okay, and they're talking about it. So hopefully you can see that. And then continue. There we go. Folding it back all the way. Okay. So now we've folded it back. And as that flux, and what you're not seeing, okay, this is the part they're not showing because they're just showing this one field line. But remember, you got all sorts of little slinkies in here, right? All sorts of little field lines. And they're getting laden as this stuff is coming in and folding this flux back. It's letting stuff into the magnetic system. So then all of this stuff is actually getting, all these particles are circulating around, and these field lines are getting heavy. Not heavy, I should say. There's getting to be more and more plasma in here. So it's pulling these field lines back, and it's making them come further and further back, pulling back this slingshot. So there are all sorts of field lines in here that they're not drawing that are no longer slinky-like. They're no longer dipolar, right? We are stretching this field line out. And as more of this stuff folds back up here, it pushes, it's filling these lobes, and it fills these lobes with plasma too. And as it fills these lobes, it pushes these field lines closer and closer and closer together. At the same time that these are getting more and more laden with stuff, because the system is open to the solar wind, and it's getting whatever that solar wind is giving it. And then this up here, it's being loaded up here too. So then this pulls these field lines together and together and together. And remember, once again, you've got that magic thing. If I can put my hands in the right place, you got that magic thing where you've got field lines pointing this way and field lines pointing this way, and they're about to touch. What happens when they touch? Boom, right? That's a slingshot being, here, before I do it, that's that slingshot again, right? You're pulling these field lines closer and closer together, and eventually, bing, and it'll shoot it all forward, right? And this whole field line will then reform, and you'll see it reform here, right? But the story has always been, I've always stopped it right here. I've never told you what happens afterwards. And that's what we're about to show. Okay, so now we're about to go, boom. See it moving forward now, watch the slingshot. Tick tock, come on, MedEd, do your thing. Look what happens though, watch, whoosh. Holy merd, slings it forward again. Pretty cool, huh? So what happens is that once you get that slingshot letting go, whoosh, we always talked about particles that shoot forward and then shoot into the poles. Whoops, shoot forward, particles come in through the tail side, the tail, and then bam, come in here. And then we always just talk about the particles. We never talk about what happens to the magnetic field. Well, that loop is being dipolarized. This is what dipolarization means. You take that slingshot, you shoot, you reconnect, shoot that thing forward, and that field dipolarizes. Okay? This is how substorms are also created. But substorms are on a much smaller level. With a big storm, you have a part of the tail, a huge, massive part of the tail letting go and doing all this at the same time. Substorms is just tiny, tiny. Just one L shell, one little field, one little bit here, there. Maybe not even the whole ring goes. I mean, it's just some part of it. With a big geomagnetic storm, man, the whole magnetic system is being laden and has to undergo this. So then as this field dipolarizes and comes back here, I don't know if it's the inertia, you have to talk to a magnetospheric physicist. If it's just the currents because you've got the particles moving and the electrons go to the dawn side, protons go to the dusk side, you've got all of this movement going on. And of course, the magnetic field is tied into the plasma. So as that moves, then you've got to have that magnetic field swing around. Okay? So if you notice, if I back this up a little bit, you'll notice that the magnetic field, see if I can tick-tock this just a little bit, as it swings around, it's not swinging around at the pole. You probably can't tell. It's actually going at lower latitudes. So that magnetic foot point, as it foot points into the upper atmosphere, is actually lower. It's not at the pole. So it's swinging back around at lower latitudes. See how low latitudes that is? So let's see if this is the one that shows that. Okay, this is the first one. Then I've got another one I want to show you. I think that's all it shows. So this process goes over and over and over again. Okay, now let me show you something else. Because this is just that one that started that. Now that I've gotten that one for you. Yeah, this is the fun. This is the fun one. Let's see if I start from the very beginning. So here, let's examine patterns of reconnection and convection for the 3 different solar wind magnetic fields. So this is the one we already did, right? And it may go too fast. So boom. Okay, it's showing you what the patterns are. Let me pause it right here. Hopefully, let me get out of the way. Hopefully this is not confusing to you at all anymore. We are looking straight down at the North Pole. This picture should be old hat for you, right? Here's the sun at 12 noon. 06, that's dawn. 1800, that's dusk. Nighttime, that is midnight, okay? Night side of Earth. Looking straight down, the Earth's magnetic field is penetrating straight down. Where's region 1 currents? Where is region 1 penetrating? Here. Where's region 1 exiting? Here, right? On the other side. Pedersen currents are coming this way. Am I correct? Right? From dawn to dusk? Hopefully my mirror isn't wrong. Okay, you guys should be able to test me at this point, right? So dawn, it's coming in here at dawn. It's going across the polar cap, and it's coming out, right? So in, cross, out. Region 1. Region 2 will be down in here somewhere, right? They're not even labeled, right? So what you don't see are the Pedersen currents. You don't see region 1, region 2 being in there. All you're really seeing is kind of the mapping of different L shells. Those are the circles, the big green, looks like green circles, gray circles, gray circles. And then the Hall currents, right? But the Hall currents are nice because they show you really what's going on. Actually, I got to be careful. No, these aren't the Hall currents. They're showing, my fault. They're the same as the Hall currents, but the Hall currents are flowing the opposite direction. I've got to be careful when I say that because now we're talking about magnetic field. These are exactly where the Hall currents are, but they're moving the opposite direction because it's the magnetic field direction. So we're seeing what happens when magnetic field near the poles ends up going from the sun, from the day side, being convected to the night side, and then after it's slingshotted, those foot points are then propagated back around. Yep. Yeah. If you look at even the words, it even says magnetic field lines are open, and the ionospheric flow corresponds to the field lines moving from the day side to the tail. And then when they come back, after they slingshot, they come back around and form day side flux again. So they start as a loop on the day side, okay, that then gets folded back by that solar wind. And as they get folded back, as I step out of the image, as they get folded back, they're being dragged to the night side in the same pattern as the Hall currents. Same pattern, opposite flow. Same pattern though, okay? So they get dragged to the night side, and that's where they get laden, and they end up, that's where the slingshot happens. And as those field lines are slingshotted forward, then they get whipped back around this way at low latitudes to form the day side flux again. Let's see if they actually show that, or if I have to start the movie over. You going to show it again? Yeah, there we go. See, look, they're showing it. The magnetic field lines are being dragged from the day side. When this happens, they're being dragged from the day side to the night side, right? As they get dragged to the night side, boom, they get slingshotted forward, and now they flip back around, whoosh. They flip back around, but they're being whooshed around out here at lower latitudes. See, they're showing it. Look at that. See how they get pulled back around, and they go whoosh. That's the whoosh. That's the whoosh coming back. Okay, no, let's stop. I don't want to talk about northward field. Let me do that all over again. Oh, poop. Let me get at least to a diagram. Okay. Okay, so let me stand where the solar wind is so you can watch it. The day side flux gets grabbed and pushed to the night side. As this gets pushed to the night side, these day side flux, they have to be at high L shell, right? Because they're right at the edge of the magnetopause. That means they must be high latitudes. So as they drag out to the tail and begin to form, and they get swung back, now they're in lower L shells. So it's got to be lower latitudes. And so when they get swung back to the day side flux, they're being swung back at lower latitudes at lower L shell. That means they have to go to lower latitudes. That's why you see them at lower latitudes coming back. But when they flip back around here to the day side, whoops, that was a really good diagram. Hold on. No. Let me wait. Yeah, perfect. So when they get from the day side, they get swooshed back, right? That's when the flux opens up. It takes the magnetic field lines all the way to the tail. And they're still at high latitudes, but then as that flux begins to come down, they're actually being squeezed down to lower L shell. And why is that? How do they get pushed down to lower L shell? Well, because all the flux that's coming in on top of them, there's other magnetic field lines being opened and laid on top of them. And another magnetic field line is open and laid on top of it. And another magnetic field line is laid on top of it. And that keeps pushing these down as like a lower, lower, lower level. Well, that lower and lower, lower level means they're getting more and more protected. Well, that means lower and lower L shell. Okay. That's how it ends up pushing them not further back, but down in latitude, down to lower L shells. So they get pushed out this way as more and more of those field lines open and lay on top, which then squeezes them down to the point where they reconnect. Boom. And that's when that slingshot gets shot forward. As it gets shot forward on both sides, whoosh. Whoops. Come on, magnetic. Come on, mirror. They're down here at low L shells and they go whoosh this way. And it comes forward and it swings back around to the day side. And when it comes to the day side, then it slowly, at the beginning of the movie, you saw this little magnetic field line that's out here, right? It's not at the front of the magnetopause, but eventually the flux gets eroded and peels it away. So this poor little magnetic field loop eventually comes out here and ends up being at highest L shell because the flux keeps getting eroded. More magnetic connection happens all the time. So this process is constantly happening. So anybody who thinks that the Earth's magnetic shield is static and isn't being eroded and ripped apart all the time, they're wrong. It's being constantly eroded at the front and being reformed at the back and brought back to the front. And then eroded again, thrown to the back, and then brought back around again. And it's just constantly going in a steady state. Okay? That creates these patterns. And of course, it happens a lot more seriously when the field is southward, right? But that doesn't mean when there's northward field that it doesn't happen. It just happens a slightly different way. And we'll get into that next. Any questions on this? Do you want me to go over this particular animation again? Because I will. It's kind of neat, isn't it? But this is definitely an advanced topic, guys. So let me know, yay, nay, you're good. I'm completely blasted. I can't do it. Tamitha, just stop the mini course now. This is horrible. You tell me. Oh, I missed something. I mean, you bring out the energy that makes this so great. Oh, far better than being in a classroom with a robot teacher. Yeah. Oh my goodness. I know a few of those. I've had to sit through them. Thank you so much. That's a nice compliment. I appreciate it. And the diagram's shown it shows the Hall currents flowing from noon to midnight. Yeah, I got it. I thought they put the Hall currents on there, and then I realized, no, they're probably putting on the actual motions of the field lines. They are opposite of one another. That's why the arrows look different. The Hall currents are exactly these same patterns, but their currents, the arrow directions are opposite. Okay, because those are currents, not motion, not magnetic field motions. But remember, right hand, left hand, electric fields and magnetic fields go hand in hand. So when you see currents and electric fields, know that you're going to see some similar movement, some compatible movement with the magnetic field. Oftentimes the opposite, just like hands are opposite of one another. So when you take your hands, you can't overlay them like this, but you can take them and put them together, right? And then they match. So they're opposites, complements, enantiomers, if you're a chemist. Oh, Mike is crackling. Is it still, guys? Do we lose anything in that process? No, it's regenerated. No, because what happens, it's the same kind of pattern. The magnetic flux can be destroyed in a sense, but it's always recreated. It is conserved in a sense. I got to be careful when I say that. Because it's always being recreated and brought back to the surface, because the generator of the magnetic field is the Earth's magnetic dynamo, and field lines are just field lines, right? The magnetic field is a constant, but it's always interacting with the stuff that's coming at it, and so it will interact and flow, and then once that whatever that is that it's interacting with is gone, then it's kind of regenerated at the front again. So it's an endless supply in that sense. I don't want to say it's a perpetual motion machine, but it is an endless supply. So, and I know I missed some comments. I apologize. Crackling. Other people are saying, is my mic still crackling? Is it still, or is it just because I had my hands and I was trying to, when I gesture or I'm doing this weird stuff, sometimes my hands get on my mic and I end up causing it problems. So let me know if your audio is starting to get clipped. Maybe battery's getting low. Yes, battery's low, guys? Because it says no. But if I'm having a mic issue, let me know. Agreed, quality is back. Okay, good. I think yeah, I think it's, yeah. So hopefully everybody understood what I was doing. I'll try not to, get my mic. But when I gesture or something, maybe I should go back to drawing on my little tablet, because that'll help. Because I don't have to contort so much. I forget sometimes I have this tablet. So, you guys, do you understand this? Do you want me to move to the next relation pattern, or do you guys need more clarity in this? Okay, how is it regenerated? How does it know? How does it know? The thing is, magnetic field lines, really, to be honest, this is kind of a limitation when it comes to explaining how magnetic field works, because honestly, there's an infinite number of magnetic field lines in this magnetic system. I can draw, it's not a limited number. Just because I'm only drawing 1 or 2 magnetic field lines doesn't mean there isn't an infinite supply of magnetic field lines in between just, L shell 1 and L shell 2. There really is. So it's kind of like, that old riddle. It says, if you can walk, you can never get to a place. You can asymptote to a place. If I decide that I draw a line on the carpet in front of me, and I decide that to get to that line, I will take a step that is half of the distance between myself and that line, right? So I take that step that's half the distance, and now I've got a shorter distance. I've got half the distance now between me and that line. But my rule is I can only walk half the distance between me and that line. Well, I take another step, and now I've lowered it to a quarter, right? But in that fashion, if I always do that, I will never reach that line, because I will always only walk half the distance. No matter how small that distance get, I will only walk half the distance between that line and me. So I will never reach it. And in that sense, you can get this sense of infinity, the idea of infinity within a finite distance. And it's the same kind of thing with magnetic field lines. There's an infinity of magnetic field lines. You never run out of them. You can always, they're always there. This is a mathematical construct that helps you understand. And so the magnetic field of the Earth's magnetic system is always there. And really, the magnetic field is everywhere. It's just a matter of how is it configured. So like inside this magnetosphere, inside this magnetosheath, or this magnetic pause, inside all this, inside the magnetic cavity of the Earth, the magnetic field is organized a certain way. But that doesn't mean there's no magnetic field out here. Of course there is. It's just organized as the solar wind designs. But here it's organized as the Earth designs. So really, it's not a matter of, are you going to run out of magnetic field? No, you won't. It's just that inside the system, the magnetic field will obey the source, the dominant source of the magnetic field, the dominant forces that create the magnetic field. And a lot of people will say, well, the magnetic field really is dominated by what the particles are doing. So you start getting into this philosophical construct. Excuse me as I step out of the frame. My mic cable is moving and I have to, yeah, it's stuck on something. I have to hold on one second. I'm having to rearrange something and I don't want to accidentally show you more of me than you want to see. Okay. At any rate, so you get into this paradigm where it's what we call a V dot B paradigm versus an E dot J paradigm. And this is where people of different camps look at the movement of the magnetic field like we're looking at now. The movement of the magnetic field is generating electric currents. And other people, and generating the direction that particles are moving. And other people look at the particles and the current systems as the drivers making magnetic field move. So in this sense here, we can look at the magnetic field in a slingshot, process as being the driver of why their currents are even created. And in the other paradigm, you can look at it as, well, the electric fields and the particles are moving, creating convections that then the magnetic fields have to follow. And so when you get into this, if you want to talk about it from that perspective, when you get into this cavity, this magnetic cavity, you don't have to worry about whether the magnetic field is going to reform and all that kind of stuff, because it's going to do what the particles tell it to do. And those particles are moving in accordance to what is coming into the solar wind, right? And what the Earth's magnetic system is, configured. You saw all those current systems, right? And they're all responding to that solar wind coming in. So in that sense, the magnetic field knows what to do because the particles are telling it what to do, right? And the current is telling it what to do. And I can say that, and half of magnetospheric physics will go, yes, Tamitha, that's exactly right. And half of magnetospheric physics will say, no, Tamitha, it's the magnetic field that dominates. So because it's this concept of the chicken and the egg, which came first, which is more important? Is it magnetic field that's frozen into the particles and the particles are dominating? Or is it the electric and electric field and currents and particles moving around that then force the magnetic field to behave itself and do what the currents and the fields tell it to do? I pick a side. I don't even begin to go into that because I'm not sure anybody can win that argument. I've seen both camps. UCLA, we have both camps. And so I was even though my particular thesis advisor was a B.V person, he saw the world, he could see the world also as an E.J paradigm and had respect for those people. And sometimes, depending upon the phenomena that you're looking at, it really helps if you can jump into either paradigm, because some things are very, very easy to understand from a magnetic field perspective, like the slingshotting, right? That's a very much easy to understand thing from a magnetic field point of view. Whereas when we get into aurora, right, and what's going on in the upper atmosphere, it's much better to think about it from the particle perspective than the magnetic fields. Magnetic fields are just penetrating. They're just going straight down. Well, that doesn't tell you anything, right? What's going on with the magnetic fields is much less illuminating than watching what's going on with the particles. So really, that's kind of the take I have, is that I'll do either paradigm depending upon, and focus on who is the driver, depending upon what the phenomena is that I'm trying to get across. Because it's much harder to think of that whole slingshotting thing from the perspective of particles in the magnetosphere. Because I mean, my goodness, you already seen particle motion in the magnetosphere is incredibly complicated. But it's so it's much easier to understand that than it is to look at the particles. But here, it's much easier to understand it from the particle perspective, and then see how that particle perspective, what that shows you about how the magnetic flux is having to do this, and how these magnetic field lines are constantly being regenerated, reformed, closed, or open, right? The magnetic field lines are still there. They're always there. It's just, are they closed or are they open? Here, as they go over the poles, they're open. Here, as they come back, they're closed. Here, as they go over the poles, they're open, right? Here, as they go back at low latitudes, at lower L shell, they're closed, right? And that, once again, is consistent with what I've talked about, right? At high latitudes, high L shell, you go to the highest L shells, well, anything higher than that, you're actually an open magnetic field. You're open to the solar wind, right? And that's what happened to this flux. It got opened by the solar wind. Then as it shot to the back, it allowed the magnetic field to close over it, because it had new field lines that were being opened, and it was pushing this magnetic field line closer and closer to the equator, where it got crushed and eventually reconnected, and it reconnected and closed it again. So it was an open magnetic field line until it got reconnected and slungshot, closed, and slungshot forward. And that's when it went to lower latitudes, right? That's as the process of it going to lower latitudes to lower L shell, right? Which is why it goes to lower latitudes. We're at lower L shell. And then it propagates or convects to the day side, where once again it starts moving up to higher L shell, up to the poles. Why? Because all that flux in front of it is being eroded by the solar wind, by that process we've already talked about, the solar wind coming in and disconnecting those field lines. So really, it's not destroying magnetic field. It's just opening closed loops and then closing again. It's that funky chicken dance, right? It's just that when you completely open it and completely close, right, the whole chicken dance then brings it around the side and then opens it up again, closes it here and brings it around to the side, and opens it up and closes it here and brings it around to the side. So it's like adding an extra step to that funky chicken dance that I did before. I just didn't want to do that then because it was a little too complicated, as you can see, right? I needed the ionosphere to kind of help show what that extra step was. All right, is that a better explanation? Did that help everybody to understand it a bit more intuitively? It's always fluctuating, yes. Oh, thank you, Maverick. Never be ashamed of yourself. You stand out in a searchlight amongst all the stars in the sky. Oh, you should be a poet. You sound very much like a poet. If you're the Maverick I'm thinking of, then yes, you are a poet. You have been so before. Touches my heart. Thank you. Whoops. I shouldn't touch my mic. Thank you very much. That's very touching. Cool to ponder on things that have mystery, yes. Isn't sci-fi cool? This is why I gave up science fiction novels and actually started doing physics. Is this cool? Can you believe you just look up at the sky and go, wow, that's happening all the time. Wow, our Earth is rad. Yeah, it is really kind of cool. I mean, there's my geeky side coming out. Oh, someone's having, oh, good, you're having an aha moment. Those are always fantastic. I love those. Those are paradigm shifts. Makes you really kind of feel like you bigger, doesn't it? It makes you feel like, wow, you're connected to the universe in some way. Yes, and thank you. Okay. Why isn't it just an EM field? It is. But electricity and magnetism are perpendicular to one another, almost always, not always, but a lot of the time. And so we have to look at each of them independently, only to understand that each of them has a role to play and that there's always like a feedback system. Because if you tug on the electric field or you tug on the magnetic field, you're going to change the electric field. If you change the electric field, you're going to cause a change in the magnetic field. So you really do, if you only look at one, if you look at them both together without looking at them individually as well, then you may limit yourself, right? Because you do have to look at them together, but looking at them at the same time and trying to make sense of them at the same time, you can kind of get lost in the weeds, because what becomes very simple in a magnetic configuration in certain instances can be unbelievably complicated from a particle point of view. And what becomes untenable in a magnetic field configuration can sometimes, depending upon the context, be extremely explicable in an atmospheric, I'm thinking forward, in a particle point of view. And no better way of explaining that than in the atmosphere, because I'm going to go through two more things, and hopefully that will become abundantly clear when it is important to look at it from a particle point of view, an electric field and particle pushing point of view, as opposed to a magnetic field point of view. And that, well, I'll just say it. Think about coupling with a neutral atmosphere. What does a magnetic field know about a neutral atmosphere? Nothing. But what does a charged atmosphere know about a neutral atmosphere? A lot, right? Especially if it's collisional, because now you're getting particles bumping into one another. Well, magnetic field doesn't care, right? Except when some of those particles that are being bumped into by neutral particles are charged, well, then that's going to change the electric field. Well, magnetic field didn't care about that, but it cares that the electric field's being changed. So now the neutral atmosphere is suddenly going to couple into the magnetic field. Well, that shouldn't happen, right? Except for the fact that you have collisions between the neutrals and the charged particles. There, in that paradigm, it makes sense. Now you understand why the magnetic field is being changed, right? But you really need to focus on what's going on only with the electric field and only with the electric field particles, then to say, okay, that's now going to affect the magnetic field. If you look at it all as a single system, sometimes you lose sight of what's really dominating the process. Oh my goodness, I've been sitting here way too long. But you guys are asking really good questions, so I want to make sure that you understand this. Okay, I see I'm saying yes, thank you. Oh, okay. You just understood what I mean by open and closed. Good, good, good. Okay. Um, Getting lost in the weeds can be fun. Yes, I do it all the time. It comes highly recommended. Um, okay. So may have to turn down the gain. Am I crackling again, guys? Or did I just tap on the mic and cause problems? Anyway, let me know. Is this magnetic cycle measured in seconds or days? This particular cycle? Oh, that's a good question. Not days. It has to be on the minute time scale. I mean, I wouldn't say this convection pattern is happening on the minute time scale. I mean, the whole thing. Measured changes are, but how long does it take for a magnetic field line to go once around? First of all, I imagine that depends upon the speed of the solar wind, because the faster the solar wind and the strength of the magnetic field in the solar wind, the more dynamic pressure, let's say, it has. The more and faster it can interact with the magnetic field. Obviously, the faster this convection pattern, the deeper the convection pattern will be, the stronger it will be. Obviously, also this auroral oval will enlarge and reach further and further down to lower and lower latitudes during a massive solar storm. Right, this entire thing. You look down at this whole thing, right, during, let's say, a G4, G5 level event. You look down at this and, oh my goodness, you're going to have aurora almost down to the equator. So, or a G5, let's say G5 event. You're going to have aurora down to the equator. So this whole thing will be the aurora oval. Imagine how big the convection patterns would be then, right? Because you're basically eroding so much flux clear down to low latitudes that this whole circulation pattern, is going to take up everything we see here. And in the south, in the southern pole, it's going to be doing the same thing, just on the other side. So you have the whole Earth engulfed in this ballet. Interesting, isn't it? As far as time scale goes, like I said, changes on the time scale of seconds, minutes. To go around once, gosh, I don't even know. I've never even thought of that. Again, a magnetospheric physicist would be pelting me with olives because they know this very well. Especially region 1, region 2 people know. How quickly does a single magnetic field line go to the tail, then reconnect, and then come back as flux on the day side? Lordy, I have no idea. Sorry, I'm futtering through any article, any teaching, anything I might have to give me some idea for a time scale, and I honestly don't have a time scale for you. I would say, I might be able to bracket it. I would say between obviously minutes and less than a day. I would think it's probably hours time scale, but I don't know. I really don't know. That is a really good question. People who would know that would be probably people who study joule dissipation, people who study the amount of energy being brought into the magnetic system and converted, right? That would tell us what level of this would be. And obviously, here's the other thing. It'll take less time for magnetic flux that's going through around in this region compared to this, or if it went to even lower latitudes, because you have to go all the way back up and all the way back, down, right? So the larger this gets, the further down you can go, and so that would affect the time scale as well. But that's a really good question. I don't think I've ever seen a paper that talked about that in particular, but that just simply may be because I'm not a magnetospheric physicist. So neat question. Wish I had a better answer for you. Audio's okay. Thank you. Okay. What's the time frame of the chicken dance from start to finish? Gosh, that's what I'm going to ask a magnetospheric physicist. If there happens to be any magnetospheric, sometimes there are magnetospheric magnetospheric physicists watching. So if you are one, identify yourself and please answer that question if you can. Otherwise, I'm going to have to go to a magnetospheric physicist and say, you know what the chicken dance is? Can you tell me how long it takes? Oh, goodness. Okay. You figure half a 12-hour period? I don't know. I don't know. I find that very intriguing question. Can successive storms keep the magnetic field open until there is enough pause to allow it to snap back? Does it keep the magnetic field open? Yeah, we've seen, and I don't know if I've shown it in these courses here, but there you can even go and see magnetic field models that show, let's say for instance, the Carrington class event, it erodes the dayside magnetopause or your dayside magnetic flux to such a degree that you don't even see anything. You see like maybe one field line that's just barely sticking out in front of Earth. I mean, it's just silly how little magnetic flux is actually a closed field line. It's because it's not because when we say eroded the flux, it just means that it's taken all that flux and folded it and opened it up and folded it tailward, because there's so much dynamic pressure hitting, and so the reconnection is so fast, pow, 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 that it's constantly keeping the flux open and in the tail. So, that's when the whole Earth is essentially engulfed, right? Because then you get all of this where we're talking about these field lines coming back right at lower latitudes. If you're down here at the equator, I mean, you're L1, right? The equator is like L1 or less than L1, L.25, really, really low. So you're almost, I mean, you're eroding almost down to the inner zone, for goodness sake, and so you're definitely keeping all of this flux open, right? It can be pretty intense, and of course that changes the whole dynamics in terms of the pattern as well. So, yeah, what is the exponent for the chicken dance? Okay, guys. So what I'm going to do is I'm just going to do a couple more things and then we'll be done for today, because this is a pretty long class. So the next thing I want to show, right, now that we understand this during a normal storm time period, right, we're about to see what happens when there's northward field. Okay, no storm, right? You'd think, oh, this just turns off. Well, no, it doesn't. It modifies. Okay, so now if we take a look at a northward field, let me get my body out of the way here. See, this field is turning northward, right? So now we're going to have the dayside flux, same kind of thing. You'll see a magnetic field line swing around. Actually, they didn't have it swing around. So what happens? Whoops. Too fast. You goodness sake. So what happens in this case? And the reason why they're not showing, no, too far. You silly thing. Why'd you do that? Okay. So what happens in this case is that the dayside flux is still here. Okay. You still have this dayside magnetic field lines. We're just not showing it. Okay. The reason why is because these field lines that are out here, not very interesting. They just stay. Because what happens is that if you have northward magnetic field, and you know what I need to, this is a really good time to use this. Okay, let's see. So you're going to be this side? No. My mirror is driving me nuts. Okay. Let me find out where. Okay, so I would do, that's up there. So it would be like this. All right, so let me erase and clean it. Keep my eye on the prize. So like this. It's a little bent. Can you handle the bent? I hope you can handle the bent. Okay, so there's your, well, and it's too far. So let me redo it again. So kind of up like that. Hey, almost. Okay, so there's the uninteresting magnetic field line. Not as well as their diagram, right? Okay, but the thing is that magnetic field, gosh, if I can draw small enough, this is why I need a stylus. Help. Let me draw it one more time. Come on. I definitely need a pen. Definitely need a pen. So there's my horrible looking arrow showing northward field, okay, at the right end. And I drew it right here on purpose because this is the edge of the magnetopause, right? So this is that highest L shell, okay, that has closed field. Anything in front of it is open. So what happens when this magnetic field comes in, right? The solar wind magnetic field comes in here. Well, you got northward field and northward field. Nothing. So maybe it'll let me do it. Right? Nothing. Nothing happens. That's why they don't show this magnetic field. Hey, this little guy is actually working, isn't it? So they don't care about this magnetic field loop, right? Because it'll just sit there and just stay there. Won't be happy about it because magnetic field, you've ever put two fridge magnets together, right? That are the same, that are the polarities pointing the same way. They don't like to be together. They keep repelling each other. So that's what's happening here. These two magnetic fields are going, and they're arguing. I don't like you. I don't like you either. And so they'll just stay like that. So then this magnetic field gets draped, folds over, right? Doesn't reconnect here, doesn't want to. But look what happens. This is magnetic field that's pointing northward, right? Pointing northward, pointing northward, pointing northward. What happens when this field line drapes over and comes close to this guy? Well, my finger's pointing in the magnetic field direction. What's below it? Magnetic field in the opposite direction, right? What do you think is going to happen? Same thing down here. Look, magnetic field is pointing this way, right? What happens when it gets draped over here? You get magnetic field pointing the opposite direction, right? What do you think is going to happen? You're going to have reconnection around in here and around in here. But look what the field is. It's not day-side flux. It's not this. It's back here. Huh, it's the night side, or high latitude at least. So let me play this. Right, you ready? It looks like it might actually happen here. And that's about right. It happens a little bit closer to the cusps, okay? Because you have the cusps of the Earth's magnetic field in these regions. Boom. Oh my goodness, what a total difference. Right, let me see if I can back it up just a smidge. So the magnetic field is reconfiguring right here, right? So now suddenly that field line that was closed, that was part of this closed loop, is now open. I mean, really open, right? It comes, this is what this magnetic field lines look like right now. It comes in like this, takes a hard turn, a U-turn, drives all the way out this way, right? And it actually comes up this way. You can't see it in this diagram, but it actually comes up here because this was like part of that closed loop. Drives here, continues, takes a hard U-turn, and goes out that way. That's a single magnetic field line. Now, as that field line comes out this way, it begins to straighten. Magnetic field doesn't like being bent. It doesn't at all. So it will exert forces to straighten out. So it will straighten out, and eventually it'll become a straight field line again pointing north, just like it did in the front. Solar wind regenerates itself too, right? You have a field line that's pointing northward. It goes all through here. It gets all messed up, blah, 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 blah. And then eventually, as it gets past, it regenerates itself as a straight line, as if this system never even existed. Pretty cool, huh? Same kind of thing as what the Earth does, right? The Earth has flux eroded. It becomes an open field, swings back around, closes itself back up again. Meanwhile, this field line is just happy, sitting here doing nothing, right? The one that played such a huge role last time in southward pointing magnetic field, southward pointing solar wind magnetic field, has nothing, has no role to play in this one. So as I continue to play this forward, you crazy thing, just moves too fast. So again, opens. Right now, see how you can already see it's beginning to straighten out because that hard, sharp turn is no longer quite so sharp, and it'll continue to straighten out. See how it's straightening out? It's trying to straighten out. By the time it gets past the Earth's magnetic system, it straightens out. And what happened to our little bit of closed flux, if we look close to the Earth? It won't let me stop. Doesn't let me stop in the right place. Try it again. It's not letting me, come on. Why don't you let me stop? See if I can just force it to be in the right spot. There, finally. So when it reconfigures, it actually causes new dayside flux to be created. So you got a new loop. Still northward, but that actually is going to make what our other northward loop, it's actually going to be forming on the outside of it. So it's actually going to push this blue loop, the darker blue loop, down to lower L shell. And the more it happens, the more loops get formed on the outside. Okay, so you get more and more loops building up that force that same blue loop, this same blue loop, to lower and lower L shell, forcing it down into lower latitudes. Radically different mechanism, isn't it, than what's happening. So what do you think that's going to manifest in the Earth's upper atmosphere? They're showing it again. Boom. There you go. There's the Earth's upper atmosphere. Do you recognize this? Shouldn't. Okay. And I'm not even going to show you what the current systems look like. This is just the magnetic field directions, right? You actually have, in this case, magnetic field being slingshot toward the day side. Remember before, with southward field, the magnetic field was being opened up and thrown to the night side. Now you're having night side flux being opened up or being closed, or being opened up and being flung to the day side where it reforms. And it gets pushed down to lower latitudes, both in the north and the south. Both on either side. See that? So for northward field, the convection patterns end up being very different, because remember, the Hall currents will likely be be the opposite as what you see here. See if they actually show. So see, now they're showing the convection pattern of the magnetic field. Whoops. Come on, where are you? There we go. So pause. Good. So now they're showing the convection patterns of the magnetic field lines being exactly the opposite, right? So closed magnetic field going to the night side, being opened up, being shot forward, and closing again down here. Once again, anything in the north, anything in the poles, it's consistent. There's still open field lines. Closed field lines are down here, but it ends up being almost exactly the opposite. So this changes what propagation will be, because it changes the current systems a bit. It changes, it doesn't change region 1 and region 2 necessarily, but it does change, it changes how aurora is formed. It changes where the currents go, at least how they're dissipated in the upper atmosphere. And we get a totally different kind of aurora. We get something called theta aurora during northern IMF. And radio propagation for northward magnetic field will also be different. Okay, very different from the night side. From the southward field. Let's see, what else do they have? And then, one thing they wanted me to point out, or they want to point out, is that you also get a secondary kind of circulation going down. That's actually, it's in the opposite direction. This is far more the way it was for your region 2 area. Very much more like what it was for southward IMF. So at lower latitudes, where you're more protected, you still get that same kind of pattern going that you had for southward IMF. It's just at high latitudes, everything changes. So this is why I say radio propagation, people who are doing radio propagation at very high latitudes inside the auroral oval. Northward IMF is a totally different ballgame than southward IMF or any other kind of IMF. Okay, changes things dramatically. And I think they'll show, the neat thing about this is that when you get a significant east or westward, so a BY component to the Earth's magnetic field when it's northward. This system will rotate. So instead of getting an arrow that goes straight from south from night side to day side, let's see if I can find, where am I? Too far. There we go. So I'm going to erase those two. So right now we have this, right? Hopefully you can see that blue line, right? You have something going from night side to day side. But if you have a westward, I think, and I may say this wrong, if you have it one way or another, you're going to have, come on, get off. You're going to have the whole system go like this. Rotate. So in that case, if we had it going that way, it would be, let me change the, that's not what I meant. Hold on, let me redraw it. So we have this pattern here, and what I'm going to do is I'm going to make it green. I'm going to try yellow arrows. No, I'll take green arrows again. And we had it going this way. Okay, and so that means the other side goes this way, right? Okay, because when you have an eastward or a westward component, instead of having it just go straight north-south, or be straight from, and I'm just going to say here from night to day. Okay, so instead of it being straight night to day, it's going to tilt. And the other way will be, it will tilt this direction. I'm going to draw it right on top. And again, you're still going from night to day, but it's going to be tilted the opposite direction. Probably too much on a single diagram, isn't it? So what happens is, and I'll erase this. Just go to that. So what happens is that instead of having something that's tilted that's just straight this way, going from night to day, magnetic field By will cause it to tilt this way or cause it to tilt this way. But it's still the same convection pattern. Is that crazy? So radio operators, if you are at high latitudes, looking at the solar wind and seeing what the magnetic field is doing, especially if it's sustained over any length of time, is a very savvy thing for you to do. Because what you'll start noticing is that propagation that you have in the high latitudes makes no sense if you look at just a day to day to day to day to day, right? Makes no sense at all because you have no idea what you're going to get, right? If you start separating out storm times, southward magnetic field, that type of thing, you're going to start seeing there's certain patterns. But if you look at non-storm times, you'll have northward magnetic field and you'll see other patterns. And then if you're able, and if you separate those two, well, then that things start making a little bit better sense. Maybe not a lot, but maybe a little bit. But then if you start looking at northward magnetic field and you start seeing big BY excursions in, east or west, then that changes things, the picture as well, dynamically. And now things may make even more sense. So if you look at your solar wind conditions and you see specifically, I have northeastward pointing magnetic field in the solar wind. That means propagation might be like this. And you start looking at propagation when the solar wind is like that, or when I have southwest pointing magnetic field in the solar wind. My propagation might look like this. And you start looking at days only when you have propagation during southwest pointing magnetic field. And then you might actually start making sense of the patterns that you see, instead of it just being a jumble and a hodgepodge. Because what's really going on up at high latitudes is an insanely complicated ballet with convection patterns and magnetic field movement that is non-intuitive and non-trivial. Does that make sense to people? Hopefully. Helping. Good. And I hope that one of the people I'm hoping to make sure I get to is Bob Hall, because he's up in Alaska and just propagation up there drives him nuts. And I'm hoping that some of this might help, especially when people are. But see, so those of us who are mid-latitudes, when I call the Goldilocks zone, we have no idea how good we have it until you take a look at this and you see stuff like this, because it's just, oh my gosh, this is so complicated, right? And I think even here, I'll go ahead and I'll keep this note too. And just, whoops. Pull that back down, because I want to go back over it maybe. But if I play this module a little bit more, now of course this module is not made for radio propagation, right? Radio amateurs, but we've kind of turned it into that, which is important. Are you playing? Oh yeah, it is. Okay. So now they're actually showing an east-west field, and I'm not going to, this is what we've already talked about. Now, see, look at the pattern. See that? And they're just showing it one way or another. And that's exactly what I just finished drawing. And of course, if it goes the opposite way, if they have, instead of an east-west, they'll have a west-east, the pattern will be exactly the opposite. I don't know if they're going to show it. Yeah, they just say the patterns are reversed with westward field. So this pattern, let me get back to it. That's an eastward field. So that is a northeast magnetic field, or actually in this case, it's a northwest magnetic field northwest, a southeast magnetic field direction, because if you notice, this convection pattern is simpler, right? It's that one for southward magnetic field, right? It's just got the two big patterns that we have gone over ad infinitum, but it tilts. Okay, so this is what a southeastward magnetic field would look, direction would look like. For southwest, the pattern would be the other way. You go from day to night, but it would be this way. Right, and I'll draw that again. And I think it's like here. Where am I? No, not quite. Here. Oh, I thought my days of a drunken sailor were over, but not really. Okay, let's see. Maybe I shouldn't do it in yellow. Maybe I'll do it in red this time. And that's there. So let me make sure I keep my eyes on the right spot. So here, and I think it's this way. No. Not this way, it's this way. Yeah, kind of. Is that right? Yeah. So now it's all tailward. Oh, poop. Tailward is here. Yes. So then the convection pattern, I've done it maybe a bit too intensely. Maybe it won't tilt quite this much. But the convection pattern will be, and I'll put my arrows in green. Hey, it's Christmas. So this is the convection pattern, not the Hall currents. This is the convection pattern of the magnetic field lines. Okay? That would be for westward, southwestward. So the tilting of the day-night, right, whether your convection pattern goes from day side to night side, that's going to be dictated by a southward or northward field. Southward field, it's going to go from day to night. Northward field, it's going to go from night to day. Okay? That's the north-south field component. East-west dictates how tilted is it from noon to midnight. How tilted is it away from noon to midnight line? If it's westward field, it's tilted, I don't know how you want to say this. You want to say tilted toward dawn? If you're going southward, it's going to be tilted more toward dawn than midnight. But of course, if you're northward field, it's going to be the opposite because your arrow is going the other way. You're going to say it's tilted more toward dusk. So see, it gets complicated. It depends upon how you define things. But it's going to be tilted this way. If it's eastward field, it's going to be tilted like the diagram beneath what I just trashed. It's going to be tilted this way, right where the white arrow is. Got it? So hopefully anyone who is high latitude or ever goes to high latitudes and wants to do radio propagation is taking copious notes, because it really does matter. And learning how to read the solar wind magnetic field to see what that field direction is doing is critical for understanding radio propagation at high latitudes. And you know what? I think today, this is where I'm going to call it, because we do have a little bit more to go through. And what I'll do is I'll do a small review of this next time. But what I will talk about is I'll talk a little bit about the coupling of the neutral atmosphere, because we have yet to even talk about the flywheel aspect of this. Because you can imagine, this is the convection pattern of the magnetic field. But underneath that, on top of that, or around that, or however you want to talk about it, the other hand, right? The right hand, left hand. This is one hand. The other hand is the electric field and the particle movement. Now, the fields and those particles and those currents are driving motion of the charged particles, right? They're driving convection movement of those charged particles. But those charged particles, if you get low enough into the upper atmosphere, they're banging into neutrals. Oh my goodness. So as they slam into neutrals, eventually they're going to start causing those convection patterns to be mimicked by the neutrals, even though the neutrals have no idea what the electric and magnetic fields are, or what the electric and magnetic fields are doing. They don't know that, but they sure know it when they're getting clocked in the face by some other particle hitting them. Oh, okay, I'll move. Okay, buddy, hold on, So they'll start mimicking those patterns. Well, if you get enough of the atmosphere mimicking those patterns, both neutral and then, of course, the electric magnetic field movement, the charged particle movement, well, now you got some inertia built up, right? You got winds, right? Well, let's say the solar wind changes and these patterns get annihilated and change into something else. Do you think those neutrals know that? Hell no, they're still moving around, because now you got so many of them moving around. They're still, even if one decides to stop, the others slam into it and keep it going, right? So it takes a while for that to calm down. That's the flywheel side of things. Right? That's the gyroscope side of things. It keeps things going because it's the inertia, and it's going to take a while to slow that down. Right? So that's part of the coupling that comes into play. And so when we start getting into the particle aspect of things, which in this case is the E.J paradigm, and you really start thinking about it in terms of this stuff, it really helps you understand how the neutral atmosphere and the charged atmosphere really can't be separated. There really is a lot of crosstalk, okay? And that is the field that we just don't have a good handle on, at least in mainstream science, because we haven't really had the instrumentation. We haven't even had the understanding of space weather. Remember, space weather has only been around for the last 60 years. So we're only getting to a point now where it's like, hey, there's a lot of coupling between these two regimes. Maybe we should look into that from a science point of view. And I think that, that's coming, but it's very slow. And it's still the physicists that are, not just the fringe physicists, but and the fringe scientists, but the physicists that are almost considered rogues in space weather and in terrestrial meteorology, right? Because you've got rogues on either side. You've got the space weather rogues that want to look at the neutral atmosphere, and you've got the terrestrial meteorologist rogues who want to look at the charged atmosphere in relation to their own fields. So you got rogues on both ends, but I think they're beginning to be, I don't know if I want to say listened to, but I think people are beginning to see that there are real scientific questions that we actually have a ghost of a chance of actually answering quantitatively, right? It's no longer just the field of speculation, because our instrumentation is getting so good, right? Because we can now use GNSS signals to probe, and there's GNSS signals everywhere, to receivers all over the ground. And we even use ADS-B, for goodness sake, and look at these receivers from different frequencies. So we're being able to probe things like total electron content, and then look at that stuff relative to, let's say, the neutral density, the neutral atmosphere, and look at winds. And so we can get electric current, winds of the charged atmosphere, which we've never really been able to see before because it's been so vacuous. We actually can probe them now with radio waves, right? With these electromagnetic signals, to understand what their wind patterns are far better on a global scale, or on a macro scale, a large scale, and then compare that to what we see with the neutral atmosphere that we can get from radar and other weather patterns. And that is the nature of what I would think is the cutting edge of meteorology now. We need to get there, and we're almost there. But it shows you, just this should show you how much just what a rich environment this is, just ripe for picking. So I'll get off my soapbox now. But all right, so that's it for today. I mean, it's, oh my goodness, been incredibly long. I knew this was going to be a long one, but I really wanted to give you this level of detail. So, and trust me, this is still just scratching the surface. But hopefully it was a lot of fun. And everybody, I'm sure, is completely exhausted by now. You can hear my voice, completely exhausted. What do you guys think? Was this good? Was this nightmarish? Tamitha's been on fire for 3.5 hours straight. Yeah, this has been epic. Oh, thank you, Nay. Oh my goodness, thank you. I was so nervous that this was going to be too much. Yeah, it's insanely long this was, wasn't it? A unified theory of physics is possible. Oh, wouldn't that be great? Yes, and things are going by too fast. Remember, don't ever try to take all this in at once. There are, this is a month's worth of teaching that I give in one day. So take it in steps. And these are archived, so please don't feel that you need to be watching this and absorbing it all at one time. I strongly advise you don't, because you'll miss too much, right? Okay, wonderful. I'm so glad. I'm seeing lots of people saying very good and thank you. Yeah, enough for me. I'm going to go watch cat videos. So am I after this, I'm sure. Too much. Okay, good. Let's see. It looks like everybody. Okay, this has been a great presentation. As an amateur radio operator, I've come away with a far better understanding of how solar winds affect my HF and amateur radio activities. You are so welcome, Jim. I'm so pleased. Yeah, that was really a goal of mine, because so many people have asked me exactly this, and I've never been able to answer their questions at the level I've wanted to. So now we do. We have something that I can refer them to. My interest began when I discovered the Soho site about 10 years ago. Oh, good, Joe. I'm so pleased. And thank goodness Soho is still up and running. You always learn so much. Thank you, Spirit. Bit by bit, I'm slowly conceptualizing more. You're so welcome. I'm so glad that this stuff is still at a level, even as complicated. Now, remember, this was totally an advanced topic. Okay, this is not entry-level space weather. And the fact that I taught it without physics blows my mind. But you know a lot of physics terms now, right? Pedersen currents, Hall currents, and you understand electric fields, magnetic fields, in terms of how they can affect things and create currents that are perpendicular and stuff. Dominic says, well, it's well worth it. Thank you. You guys are so welcome. Jackie, Adam, I'm so pleased. Oh, thanks, Jerry. You're so kind. I appreciate you saying that. Josh, thanks. This has been an incredible presentation. Thank you, Josh. Oh, and I can't thank you guys enough, especially everyone from Patreon. Look at the tools you guys have allowed me to have now. Was this cool? Did the tools make it? I mean, it sounds like the tools really helped, and anything that helps facilitates learning. Like, I couldn't even think about how I was going to do this class without these tools, because how was I going to draw and show without being able to mark up these diagrams? So this has been, even as clunky as the whole interface has been, I'm very tickled with it. I'm smiling, loved it a lot. That's so great. Thank you, Alan. Thank you, Jerry. Appreciate it, guys. Let's see. Rewatching. Yeah, definitely take your time. Rewatch. Don't feel that you have to absorb it in one go. Pluto should never have been demoted. I agree. Pluto gets the grandfather clause. It's totally a planet to me. I don't care what anybody says. Pluto is grandfathered in. Still riveted 3 hours later. Oh, that's great, Alan. Thank you so much. My gosh, that is such a huge compliment. You learn something new every time I talk. Good. I'm so relieved, because I was so nervous this was going to be too intense. I mean, I get pelted with olives enough as it is from people who say, my gosh, your stuff is too hard. But it sounds like this ended up being pretty good. You learn by sticking a screwdriver in a plug when I was a kid. Yeah, well, I think this is the analogous side of that, right? In terms of what it does to your brain. It's like shock therapy. You don't need shock therapy. Just go watch one of Tamitha's mini courses. Oh, oh gosh. Okay. Um, yes, the chalkboard is great. Fantastic. Okay. A lot of tools. Great show. Good. Thank you, Andy. I'm so glad you guys found this useful. Um, right on. More Coke machine. Oh my goodness, no. Next month. I will answer, I'll stick around if anybody has any extra questions. I will stick around for a few more minutes. But I at 4 hours I turn into a pumpkin, guys. So, and I'm sure Jerry and Mike are going, "Oh, Tamitha, enough already. Please, we want to leave. We have lives. We don't want to just stay here and be your moderators as much as we love you. Enough already." So I'll stick around for just a minute or two for any final questions, but we're definitely wrapping it up, folks. Yeah, Grandpa. Yeah, definitely Grandpa Pluto. You did great the last hour. Okay, good. I'm so glad you guys liked it. And yes, again, any as a matter of fact, let me check Patreon to see if there's any questions that have been posted on Patreon. For all people who are on Patreon, if you have questions that have been unanswered or you come up with questions later, still post them or send me a direct message, however you want to do it. I will absolutely answer them. And if I need to have some other, like behind the scenes, instruction like this, like a little mini course addendum or whatever, just for Patreon folk, I will. So we can go over some of this stuff in more detail. Lord knows I need more practice on my little pad. See my little diagram. I got fingerprints. Look at how messy that looks. Good night. That looks terrible, doesn't it? Where's my Windex? And I have to get a stylus. But yeah, I will be more than happy to get more practice and help you guys learn more. So let's see. Okay. I see a couple questions. It didn't feel like a long time at all. Thank you. Does any of this affect where radio blackout occurs? Not really, because a radio blackout it occurs for two reasons. Three reasons. One, you get a radiation storm that will affect all the open field lines. Two, you get it on the day side where if you can see the sun, the sun will get you. And then three, it's radio. It can also be a radio burst, so that affects all the satellites. So that really doesn't have much to do with the ionospheric convection patterns. But that's a good question. Hey, Infodog. Hey, howdy. Good. I'm glad you were with us for this. You're welcome, John. Your help and teachings are very appreciated. You're very welcome. Yeah, Mike is tired. Mike says, "Oh, I'm getting out of this." Okay, I thought this was intellectually stimulating. Oh, that's wonderful. Thank you, Mike. I appreciate you saying that. Right, Lisa. You're waiting for clouds to move. Yeah, no. Well, if only these convection patterns could blow the clouds away. We wish. Oh my goodness, yeah. The tornadoes are horrible. Stay safe if you're in one of those. If you're in Tornado Alley, please stay sane and stay safe. Joe Rogan interview, right? We need one of those, don't we? Read your fingerprint codes for more information on your iPad. Cute. Okay, let me check really quickly. Oh, good, Bob, you're here. Awesome job. Hopefully that stuff helps you. I wanted to make sure that you got that. Let's see, where is my Patreon? Has anybody on Patreon? I lost my thing. Has anyone on Patreon asked any questions on the feed? So let me just take a look real quick. Josh, you say, I wonder if there is a way to show the live NDI source from your OBS on your iPad. I know, that's what I'm trying to work on, Josh. I'm so trying to work on that. I mean, I was thinking of doing it as a, I'll stand out back in the light for a second. I was thinking of having a PDF and then projecting the PDF here instead of, but I mean, look, obviously for the comment module, that isn't possible. I can do it for my PowerPoints, but like, look at this, most of my drawing, well, at least half of my drawing ended up being on the comment modules. So that's the only problem, is that I'd have to be able to clone the composite, not the composite, the background for my, which is really the NDI, isn't it? It's really the NDI output from my computer. I'd have to clone that back to there, and maybe there's a way. I know there's a way to do it if I'm on a computer. I don't know if there's a way to do it on a mobile device and have that be the recipient through NDI, but maybe so. That should be tools that we look for. Because if I had that on there, oh my goodness, that would make a night and day. I'd be able to draw very easily, and we wouldn't have to do any of this weird me hunting for where the appropriate location is on my iPad. But I think some of that will help when it stops being mirrored, because I have a much better spatial acuity. I'm good with spatial acuity as long as I don't have to flip it. If I have to reverse it, then it becomes, like, whoa, wait, left is right, right is left. It becomes hard. But that's definitely a worthy endeavor to search for. So thank you for that. Yeah, Karen Figgins says 3 hours and my brain is saturated. I did learn something though. So that's so sweet. So I'll catch the rest later. Yeah. This was a tough one, guys. This was a hard course. So I appreciate all of you sticking in with me through the whole thing. And again, if you've got overwhelmed, please know that is so normal, especially here. The fact that you've actually made it this far at all makes me bow to you. Please don't try to absorb all this material in one go. You're talking to someone who's done this for 20 plus years. So, and this was a deep dive. So I'm very proud of all of you who said you actually understood anything that I had to say today. I can't be more thrilled. This community you guys just blow me away. And if I keep talking about it, I'm going to tear up. You guys just impress me in so many different ways. I can't even tell you how grateful I am to be a part of this. So thank you. All right. If I don't see any more questions, guys, looks like I've questioned everybody else. Yeah, don't use a pencil. It's magnetic. Cute. Yes, and spirit prayers for everybody affected by tornadoes. Agreed. Okay. So I see a lot of speculation. Good. I'm hoping that this is helping. I'm hoping this is helping people like start thinking and opening their minds to think about connectivity in other ways. So it looks like I'm seeing some of that now. Was your course this intense at Berkeley? I never taught at Berkeley. I've taught at Millersville University. I've taught at UCI, and a little bit at UCLA, but not very much. And no, not yet, but I'm probably going to get into this level at Millersville for my next set of students. So if any of my students are watching, you're in trouble, because I have tools now, so I can actually go into things at this level of intensity. There are other things I teach though at Millersville that are extremely intense that I don't teach here on YouTube. And I also go into an astrosociological side of things that I don't teach on YouTube either. So there are reasons for, if you're interested or thinking about joining my Millersville students and taking the courses at Millersville, you will find there's a lot more at Millersville than there are on the YouTube classes. So, thank you, Chuck. You said I'm a great teacher. Much appreciated. And thanks, Smash Ash. Rock on, Tam, with the best wishes. May the solar wind be at your back. That's wonderful. Jerry wants to leave. His dog is crossing his legs. Okay, guys, I gotta go. Because I'm losing my moderators. They're done with me. They're gonna send me some choice texts, I'm sure, for my 4-hour. This may be the record, by the way. Okay, guys. Oh yeah, Lisa, you're the next student. That's right. Oh my goodness, you're gonna love it. Yes, astrosociology. It's how pop culture integrates space weather and everything to do with space. Really fascinating stuff. But that's exclusively available at Millersville. I don't teach that on YouTube. So, all right, guys, I am letting you go. Thanks so much for sticking with me. Thanks so much to my moderators, both Jerry and Michael. I adore you both. And you're going to get some Christmas presents from me. So be ready for that. And I will talk to you all soon. Okay. Stay safe till next month.